And then after the break, Michael and Shella will go and provide more details on the interpretations we can have of these fluctuations of resting state functional connectivity and activity. And Dan, who has been leading the writing of a review paper recently on dynamic functional connectivity, will tell us more about the remaining open questions and challenges. So let me, with this, thank all the speakers for accepting to give a talk here, and thank you all for attending. The first speaker will be Giulia Preti from EPFL in Switzerland, from Dimitri van der Wild's lab. So, Giulia.
Hello, everyone. Thank you for being here. Can I just ask an information? How do I switch the slide to the? Come vado? Okay. Yes. Thanks a lot, and yeah, thanks for being here in this early hour today. So I will try not to bore you too much with this first talk of the symposium, in which I will go over the efforts that have been done in literature to go beyond the framework of static functional connectivity and to appreciate the temporal fluctuations of functional connectivity. But first, we will have a look at the basics of functional connectivity to be sure to be all on the same page, and we'll introduce some important terminology that we'll be using for the whole workshop. So it's really important in order to avoid confusion in this field. So functional connectivity. Functional connectivity is defined as the statistical dependence between time series. What does it mean? So usually what you find in literature is the following. We have a parcellation of the brain, so usually based on an atlas. We subdivide the cortex in specific areas, and then we compute regional time courses that can come from, for example, from functional MRI. Simply by averaging all the voxels that are within each region. And then these time courses, normally we consider the whole length of the acquisition, and we compute pairwise correlations. So it means that for an acquisition that can be resting state, so while the subject is not doing anything in particular in MRI, we obtain a functional connectivity matrix, which looks as follows. That is an ROI by ROI matrix that contains all the correlation values, so pairwise, so for all the pairs of time courses. And this is what we refer to as static functional connectivity, static functional connectome. So static functional connectivity has two main properties that we want to focus on today. The first one is that it's averaged. So you will all agree that it's an averaged measure in the sense that you consider the whole length of the time course and then you produce one measure, one correlation. So in fMRI experiments, this means that you have one functional connectome that describes or tries to describe the behavior, what is happening in a period of that usually goes from 5 to 15 minutes. So you can imagine that it's an average picture of what is really happening. And then the second property is being memoryless, meaning that it's invariant to reordering of time points. So if you have two time courses, for example, which are correlated by a specific correlation coefficient rho, and if you permute time points, so in the two time courses, then the final two time courses will always be correlated by the same coefficient. So this is because every time point is considered as an independent observation, and we don't model the links, the variations between subsequent time points. So in this sense, we consider it memoryless or static. So efforts to go beyond this framework of static functional connectivity basically see these two directions, so relaxing these two properties, and we go into two different directions that we'll describe now. So in the first case, if we relax this property, so we don't want an average measure anymore, but we want something that changes in time, what we obtain is a time-varying functional connectivity. So there are several approaches that actually do that, and for sure the most commonly adopted in literature is the sliding window approach. So in the sliding window approach, really briefly, instead of considering the whole time course, we select one specific window, we compute the correlation between all time courses, and then we slide the window. So in this case, we obtain a time course of the correlation coefficient. And if we do that for all pairwise, for all pairs of correlation, what you get is an evolution of the functional connectome. So in this case, you can observe changes in functional connectivity because you have one connectome per window that you produced. So normally, this amount of data that is getting bigger and bigger because now it has the dimensionality of connections in time, it's summarized with factorization techniques of all these dynamic evolving connectomes in order to retrieve what we call connectivity states. Just briefly, what you have to pay attention to is that depending on the technique that he used, for example, k-means clustering he used a lot, PCA was experimented, so the interpretation changes. So these states have different properties. For example, they can be temporally overlapping, spatially overlapping or not, depending on the technique that is used. So it's just to warning to be careful in the interpretation based on the technique which is used. So then if instead we relax the memoryless property, we are saying, okay, we want actually to model the variations between time points. And in this case, these approaches we will refer to dynamic functional connectivity. And one example of that is provided by autoregressive models. That's here really briefly, that they were used to model dynamic functional connectivity. And in this case, what we do is expressing the volume and fMRI volume at time point t as a linear combination of previous p time points. So the fMRI volumes that you see here vectorized, so it's just a vector of n regions, at previous p time points, p being the model order. So here, the dynamic feature that we are interested in are the coefficients of the matrix A that we estimate. That actually tells us about the dependency between two different time points, so between two time points t and time points t minus L. So if you want, it provides with a sort of dynamic version of the correlation. Dynamic in the sense that we just expressed, so having memory, a measure that has memory. So today, I will go over the main approaches that have been proposed in literature with this subdivision. So we will describe some time-varying approaches, and then we will move to dynamic approaches. So the sliding window that we already introduced, we will look a bit into the limitations and describe also a framework that has been proposed more recently that moves from sliding window to the analysis of single frames. Then we will see the revisitation of these frameworks, which is the one of coactivation patterns, but with a dynamic twist. And then we will see how you can apply autoregressive models to compute dynamic markers of functional connectivity. So first, if you go back to sliding window, as I said, it's for sure one of the most used in literature, I guess also for its simplicity. It's really simple, right? But of course, it's not perfect. It has limitations and there is a great effort, again, in literature in order to overcome these limits. So the first ones are for sure the one regarding the choice of the window parameters. And then we will talk about the choice of the parcellation, which is also important. So regarding the choice of the window parameters, unfortunately, there's no golden rule and there's no optimal solution that goes in general, let's say. So it depends really on the application. But what we can say, especially on the window length, is that the choice of the window length that will be, unfortunately, a priori, must be a trade-off between sensitivity and specificity. So what does it mean? Sensitivity, because we want the window to be short enough to record true positives, right? So to record the real fluctuations on functional connectivity, as if the window is too long, then we will lose what is inside. Everything which is inside is averaged out. But then at the same time, specificity, because the window must be long enough to detect only real fluctuations, as it was shown that with two short windows, we have spurious fluctuations that we record as correlations. So for this second constraint, we can give a rule of thumb, which is to choose a window that is at least 1 over the minimum frequency present in your original time courses. And this is a parameter, this f mean, that commonly depends on your pre-processing, because normally there is the high-pass filtering of your original fMRI time courses. So just to be careful in choosing a window that is at least 1 over your high-pass frequency cutoff if you perform the high-pass frequency. And then regarding the window shape, so the most simple rectangular window was used a lot, especially at the beginning, and now we can also find often a tapered window that weights less the boundaries of the window, so in order to avoid some noisy, peaky, let's say, noise peaks at the borders. Then regarding the choice of parcellation, this doesn't only regard sliding window, but in general functional connectivity studies. There are many parcellations available. Some of them are based on anatomical, some of them are based on functional data. And so, of course, it's always an a priori choice that you have to make. And it was shown in literature, unfortunately, that this choice can actually have a big impact on your final result. So what we were trying to do to solve this parameter, so what we could do is try to go without parcellation. So in that case, you have to analyze voxel-wise fMRI time courses from gray matter, but it's still a lot of voxels. And the problem here becomes a problem of dimensionality, because okay, you do your sliding window as usual, but for every window, when you go and try to compute this connectome, you have a dimensionality, a storage. I mean, you cannot even compute or store this voxels, time voxels matrix. So a solution that we proposed a couple of years ago is the following. So instead of computing a functional connectome for every window, you could compute what we call eigenvector centrality, which is just the first eigenvector of each functional matrix. So being the first eigenvector, it has a dimensionality, it's a vector with dimensionality, the number of ROI, so we don't have a dimensionality problem anymore. And it gives you an approximation of your functional connectivity. So it's a dominant pattern, the first dominant pattern of the functional connectivity. Yeah, basically the key point here is that you can retrieve this eigenvector centrality, so these vectors, without computing the original functional connectome, so keeping the FC matrix implicit. So you skip this step, basically. You just have to be happy with the approximation that you're giving, which is a rank 1 approximation of functional connectivity that might be enough for your purpose. In fact, in our case, it was basically, because then we validated this approach in this way. So actually we asked ourselves the question, okay, we want to go voxel-wise, right? We don't want to a priori select any parcellation. But indeed, maybe the voxel-wise dynamic features, so the dynamic features of one voxel are really similar to the neighboring voxels. So which is the resolution that we really need in order not to have redundant information. So the highest resolution possible that is still adding some additional information. So in order to investigate that, we aggregated the voxels that showed the exact same pattern in terms of time-varying functional connectivity, in terms of eigenvector centrality. And doing that, we ended up with a long-range parcellation, which includes 37 distributed patterns. It's the one that here you see on the left. And it's the first whole brain parcellation that is derived by voxel-wise time-varying functional connectivity. And then you can also obtain a second version of this parcellation, a finer scale version, just by subdividing the distributed patterns, the original patterns, into contiguous regions. In this way, you get 449 contiguous regions, and in the second version on the right, the difference is just that you can appreciate this subdivisions of specific areas. For example, here you see the cerebellum, the precuneus, and the results when you analyze this subdivision, so this parcellation was consistent with previous analysis, but with additional information of time-varying functional connectivity. So the advantages are that it's a completely data-driven method that solves the well-known issue of a priori choice of an atlas. So you can use the eigenvector centrality trick in order to go with voxel-wise parcellation, voxel-wise time-varying functional connectivity, or you can use this parcellation if you want still to adopt a parcellation, but that includes the most information possible in terms of functional connectivity, because it includes the temporal fluctuations. Then, more recently, let's say in the last few years, there was a switch of interest, let's say, from the sliding window to frame-wise analysis. So let's see what it means. So it's better maybe with a visualization. So if you consider 2 time courses, as we said, normally with stationary approaches, you would have an average over the whole time course, right? So you get an image of the connectivity, which is really blurred. With sliding window techniques, this problem is reduced because the window is shorter, but still you have an average inside the window. So you get an image that is a bit less blurred, but same problem of averaging. So the question now is, are there key points in your fMRI time courses that actually encode the capture imported events? So could we just select these key points and then go ahead with our analysis without any average? And this was the idea behind the introduction of the technique called co-activation patterns, which was inspired by the previously introduced point process analysis, which is actually based on this concept. So selecting only interesting frames and then perform your analysis based on that. In this case of CAPS, your selection is based on a seed ball time course. So you have a region that you're interested in. For example, in resting state might be the posterior cingulate quarters, PCC, which is a region, a hub of the default mode network activated during resting state. So you have a time course and you select time points based on when this region is active. And then your aim is actually to see what other regions are co-activating together with the seed, so together with the PCC, or co-deactivating. So to do that, you just select the frames at these time points that overcome the threshold, and you perform a k-means clustering of these frames. The centroids of the clusters are the patterns that we called co-activation patterns. So in this case here, what you see, these are the PCC-related caps that were obtained in the original paper where this technique was introduced. And the co-activation patterns include, as I was saying, regions that recurrently co-activate or co-deactivate with the seed for limited amount of time. So the advantage with respect of conventional techniques is that we can see that known resting state networks are decomposed into multiple sub-patterns with different temporal occurrence. So maybe a network is not active for the whole time, and in this way it's a first attempt to try to recover patterns that are active just for limited amount of time. But it's still static, okay? It's still on the time varying approach. It's not dynamic in the sense that being based on correlation, we are not modeling the interactions between time points. An effort to model actually like a dynamic extension of this framework of CAPS is represented by innovation-driven CAPS, so ICAPS, that were introduced a few years ago. In this case, the dynamic twist is given by the fact that we are not clustering frames, the original frame of fMRI, but we are clustering innovation signals. So innovation signals are represented by the first derivative of a version of the bold, which is denoised and deconvolved. These are the one that you see here in magenta, while the black one is the deconvolved bold. And in being the first derivative, you are actually modeling the changes between time points. So it's what we call under the umbrella of dynamic approaches. And in other words, you're interested into transitions of the bold signal rather than peaks. So you want to see if regions that change their signal together instead of regions that are active together. So you don't care about the baseline, so where the signals were starting from. These are examples of the innovation signals at specific time points in which we have, for example, what you see in red is chain co-activating, as you say, as we were saying before, and what you see at the same time in blue is co-deactivating. So if we use these signals as inputs of our clustering, we obtain a repertoire of functional networks. So these are the ICAPs, in which you for sure recognize resting state networks that we know. So the ICAP with longest duration is the default mode network, so okay, makes sense. It was still resting state. But at the same time, we can, given the fact that we are doing a dynamic analysis, we can have access to subsystems of the default mode network. So the default mode network itself, as you can see here, is split into sub-portions that actually have different temporal properties and that we were not able to disentangle before. So now other dynamic approaches, as I was saying before, can be based on autoregressive models that, as you can see here, we take back the equation of the autoregressive model. In this case, we have an order 1 autoregressive model, so it means you are modeling the link between successive time points, so time t and time t minus 1. And these type of models, in this type of models, the DFC markers, so the dynamic functional connectivity markers, are encoded, as we were saying, in the coefficients of the matrix A that you estimate. And these type of models were shown to actually be useful in functional connectivity, so to explain functional connectivity fluctuations better than static functional connectivity and hidden Markov models. And then in a more recent work, always by Raphael, what they were looking into is if these models could also explain the behavioral variance, so if the behavioral relevance of dynamic functional connectivity. And so in order to do that, in this analysis, both static and dynamic functional connectivity assessed with autoregressive models were linked to 58 behavioral measures using variant component model. And the first thing you see is here on the A, in figure A, is that on average, when you look at the whole brain and over all phenotypic measures, dynamic functional connectivity features are able to explain more the behavioral relevance with respect to static functional connectivity. So there is additional information that we can retrieve. But then, interestingly, when we look at the single behavioral measures, we see that different types of behavioral measures are explained differently by static and dynamic functional connectivity. So in particular, there are behavioral measures that reflect task performance, like fluid intelligence, working memory, that are better explained by dynamic functional connectivity measures. And it might be given the fact that these type of performances involve actually complex interactions between networks at shorter timescales, so that they would be lost in a static type of analysis. Instead, other behavioral measures like meaning of life, perceived stress, loneliness, these are more like trait-like properties of the person that are not characterized by such short dynamic, and these are shown here to be equally well captured by dynamic and static functional connectivity. So it's interesting because this shows actually the complementary information that these two type of approaches could give us, depending on what we are investigating. And then last, I would like to show you another extension. We always start from autoregressive model, and it's another recent work by Raphael, where actually we can have what is developed is a dynamic extension of the conventional component analysis that you for sure know, like ICA, PCA, that usually are applied to fMRI time courses. So in this case, components are represented by eigenvectors, so by the eigendecomposition of the matrix A. So it's thanks to that that we include dynamic features in that, because they come from A. And in fact, for each component, we can retrieve both a pattern, a spatial information, which is given by the eigenvector of A, and a temporal information that is given by eigenvalues of A. So each component can be associated to a temporal characterization that is characterized by a period and a damping time, for example, computable from eigenvalues. So differently from conventional component analysis that in our terminology can be considered static. In this case, we obtain spatiotemporal modes that can be characterized also temporally, basically. So just to give you a further insight into this, it's just a visualization that you might appreciate. So if you have RI time courses and we select one time point, so we have an n-dimensional vector we set, and this can be visualized as a point in an n-dimensional space. So you have another one. So all time points are represented by a cloud of points in the n-dimensional space. And then what conventional component analysis does is finding a new space of components that is always has only the spatial dimension. Okay, so it looks at how points are distributed in the cloud, in the new space. But then what we are interested in doing, as we said, is modeling the link between successive time points, and this corresponds in our space at links, so the evolution between points. So we would have, instead of only spatial component, we would define spatiotemporal components that look not only at the distribution of points, but also at the evolution in time of these components. So the first two dynamic modes that are retrieved with this technique are the following that you see here. So you can recognize resting state hubs, let's say. So in the first case, we have an anticorrelation between default mode network in red and task parietal network in blue. But in the second case, what is interesting to see is that you still have regions of the DMN, but it's subregions of the DMN, so lateral subregions and prefrontal cortex anticorrelating with visual. And so we can say that, like before, so the other dynamic approach that we mentioned, so like with ICAPS, you can have access to the subsystems of the DMN, so subportions of DMN that are temporally characterized differently from each other. And with this method, you can actually give precise temporal characterization, as you can associate each component with a period and with a damping time. In this case, these both have infinite period, meaning that they don't oscillate, but they have a specific time they are active and then before fading. So with this I conclude, and the take-home message that I would like to give you is that in resting state, when we record resting state, the brain is dynamic, it's active, so it makes sense to explore it with dynamic time-varying or dynamic functional connectivity, so going beyond the static approach. But there is a plethora of methods to do that. So just, this is a bit of a warning, so you always have to find a trade-off depending on your needs. So you can have data-driven methods that we saw today, model-based methods, dynamic or time-varying, and different methods can be more right, let's say, for your specific application. For example, if you have to correlate with behavioral data or other modalities like EEG and so on. And also the brain states that you are commonly retrieving, also there you can have a lot of methods in order to retrieve them. So yeah, of course you choose the one that is more suited for your needs, but then you just have to be careful in the interpretation. And with that, I thank you and my lab, and of course I look forward to questions if there are.
Okay, thank you, Giulia. So we have time for a few questions. Yes?
Of autoregressive models? Sorry, it's Casorso 2019, so it's a recent paper of Rafael that just came out. You meant that, right? Yeah. Mm. Really interesting paper.
Yes.
Oops. In these autoregressive models, you mean? I leave the word. Yes.
Yes.
The expert can.
So how you test your data if it is stationary, or you make some assumption about this?
So yes, the model needs to be stable so as to not diverge. So this implies that it will be stationary. But stationarity in the statistical sense is not something that is in contradiction with observing fluctuations. So that's something that we did in a 2017 paper, the neuroimage that Giulia also mentioned, where you see that stationarity does not prevent from capturing these fluctuations that are meaningful, that are real, but yet stationary. So it's not a problem to have a stationary model of, like a hidden Markov model is also a stationary model from a statistical point of view.
But you encode fluctuations, basically. So this is why we were careful in not talking about stationary functional connectivity, but static functional connectivity. And we didn't mention anything about stationarity because you can actually appreciate temporal changes even there.
Do you directly use the data or you make some pre-processing when you use this method?
Yeah, the data is just HCP data which are pre-processed. So we don't, it's not simulations, it's real data that are pre-processed with the conventional fMRI pre-processing.
Not do any pre-processing about the time series. Like
The fMRI time series. No, it's just, you know, you don't make any, you mean any specific pre-processing for?
for the selection.
No, they are not, nothing is done. Yeah. You're welcome.
Yes?
I would like to ask regarding your Voxel dynamics.
Yeah.
How would you deal with group analysis?
Yeah, this is a really interesting question. So I repeat it. So how you deal with group analysis with the voxelwise method? So first, I went really fast, so maybe it was not clear, but it comes, I mean, it is a group analysis. So basically, when I try to, let's say, aggregate voxels based on their feature, the step before is a concatenation of all windows and subjects, and we retrieve these eigenvector patterns. So we aggregate the eigenvector centralities for, you can do it for a population. You can do it for one subject, but what is interesting is doing it for a population. So in our case, it was for 54 subjects, healthy subjects, so that you get a picture of your population. The problem is that, I mean, it's not the problem. Like the issue to address is a bit in group analysis. So how you do it when you have two groups. In that case, I mean, depends, I think. So you can think about how, if you want to use it as a conventional atlas that just encodes the time-varying functional connectivity information, then you can estimate it just for the healthy population and then apply it to the patients, I think. But then this must be dealt with, I think, case by case. I mean, like normal with atlas and parcellations, but it's already a group analysis, yeah. You're welcome.
Okay, let's thank Giulia again.
Thank you.
And the next speaker is Manjari Narayan from Atkins Lab in Stanford. So Manjari is a statistician, and she will tell us a bit more on how we can use null models to assess the statistical significance of these fluctuations that we observe.
Great, thank you, Raphael. So thanks to Giulia for setting up the topic of discussing how to interrogate our interpretation of fluctuations in time series and whether or not there is time-varying functional connectivity. So so I'm going to have some polls. Oh, how do I go back? Okay. Okay. So there's the poll. So if I have some polls later on in this later on in the talk, so be sure to know how to access audience response. And when you see a poll, Raphael will unlock the poll, and you'll be able to answer questions. Okay. So, as mentioned earlier, fMRI data is actually a time series. Yet, and just notation-wise, we have volumes or time series by brain regions or voxels. This is how we're going to represent fMRI time series in my talk today. And what we observe is this data matrix of fMRI time series, but yet the underlying assumption is that this data is being generated by some unknown network model. And so the statistical point of view of where our data comes from is that there's an underlying statistical network model that generates our data and our observations. And the network is actually unknown, and it is related to the probability distribution that the data comes from. So this is the underlying premise of how I'm going to be talking about functional connectivity. So from this perspective, functional connectivity is actually the unknown network model that generates our data. And so the dominant paradigm so far has been that we ignore the time series structure in this data matrix. We always assume that our individual observations of our data are independent and identically distributed from this network model. And when we make this assumption, then the way we compute correlations on our data, the sample, linear Pearson correlation, is a perfectly good estimate of this kind of network structure. But we're overly fond right now of this IID model of the brain network. And recently, and I think there's a reason why all of you are here today, is because there's a tremendous interest in going beyond this dominant paradigm of looking at the IID network model or correlational network model that we're all used to. And so the perspective I want you to take away from my talk today is that there's really two modes of thinking about functional connectivity in fMRI time series. And one is making inferences and hypotheses about only the things we observe. And only the things we observe are the time series themselves or the features of the time series. And we can strictly make only inferences and observations only about what we observe. Or we can actually have hypotheses about the things we don't observe and try to use procedures to draw conclusions and inferences about the things we don't observe. And so it's really important to be sure what kind of technique and what kind of inferences we're drawing. And I think a lot of the controversies and discussions in the literature about time-varying functional connectivity and fluctuations are all built on, are we treating these separately, or are we kind of blurring the lines between them? And that's when things get confusing or seem apparently in conflict. And if there's one thing you're already going to take away, it's, I hope, more clarity on these two modes of thinking. And why does thinking about these two classes really matter? Because there's one important question is, are we using rich enough models to model our fMRI time series, or are we leaving information on the table? So from this perspective, what matters is, are we explaining the things we observe well enough? But on the other hand, once you fit the models to our data, as scientists, we always want to interpret the parameters we fit to our data. And in that context, we need to think more carefully about, well, what do the parameters mean? And do they mean what we think it means? Right? And that's where we need to care about hypotheses and drawing inferences about the parameters. So a lot of the controversies today go way back, almost a century ago. So just consider two sinusoidal signals. There's no noise, no nothing. But if we were to compute, sliding window correlations in this context, infinitesimally small, what we would notice is that you would observe on the right-hand side time-varying correlations. So the local correlations are non-zero, right? You just saw it looked like a square wave. But in fact, when you look at the whole time series, they're all the two time series are completely orthogonal to each other, right? There's no communication between them. So Giulia, who was very early in the days of time series, already noticed this funny thing about looking at correlations local in time as opposed to looking at the series globally. And what he did was he actually did this analysis where he varied the window length. And when the window length was really small, the size of this local correlation was really large. But when the window length was really large, almost 90% of the full time series, he noticed that it was really, really small. So he made these observations, and he called these nonsense correlations. That's, in fact, in the title of his paper. And so this, in fact, the same issue has been in a bunch of recent papers that Giulia referenced, work by Martin Lindquist, and some others have also identified this window length issue. But the window length issue, the thing to note here is there's no noise. This is an issue about conceptually what is it that we're defining. So, and the trade-off here is that thinking about a correlation local in time might itself be an ill-defined concept in that here's two time series, there's clearly no information between them, and yet if we look at it in the wrong way, it might seem like there's something going on, right? And this is I'm not going to talk about multi-scale and time frequency models in my talk, but I want to throw it out there that if you look at your data in the right way, in the right kind of modeling framework, such as at multiple scales using time frequency methods, you won't see these illusory correlations. So that's something to keep in mind. And I think some of the other talks today will talk about multi-scale approaches. So another recent proposal that came out recently was to suggest looking at, instead of just looking at sliding window correlations over time, to look at kurtosis. So in this paper by Lohman, what they looked at is they simulated a time series where there were two states. The eyes open state simulated from real data based on characteristics of real data during eyes open. And in another simulation where there were two states, eyes open and eyes closed, and there was a transition that happened. And what they suggested was, rather than looking at sliding window correlations themselves, let's look at the variance of the variance. Let's look at how the sliding window correlations are varying. And let's use kurtosis as a measure of what's changing across time. And so what they were able to show was in this that if you look at kurtosis as a measure, then in the two-state phenomenon, in the two-state simulation, you see higher kurtosis happen right when the states change than not. So what is this proposal? What is this really telling us? We're looking at a statistical summary of our observations, which are sliding window correlations, right? So what is this proposal of using kurtosis as a measurement of fluctuations in the data? Another recent paper that came out that highlighted a very important, crucial point. Any test statistic that we use to draw inferences about our data, it needs to be monotonic, meaning it needs to increase as a function of discrepancy from the null. So if the null is that the data is stationary, that nothing is changing, then as there's greater change away from that null, then the test statistic should proportionally be greater also. And in this paper by Miller that came out recently, what they showed through some very nice counterexamples is that, you know, when you have outliers in your data, as in case 1, then kurtosis is really high. But in cases 2 and 3, you can see that there is, you know, the oscillation is changing. This is like clearly, there's something about the covariant structure of the data that itself changing. So this is strongly deviating from the null that the data is stationary, but kurtosis is decreasing. It's not increasing. But instead, if you look at this kind of data in time frequency domain, and if you look at another spectral measure that they propose called phi, this would actually increase as the data is getting more non-stationary. So we really need to think about how we're framing and conceptually thinking about what we're measuring. So these are some controversies that came out recently. So what I want to do is delve a little bit more deeply into this kind of thinking about our models and test statistics of what's really changing in our data. And just to give you a brief overview, like there's a really huge spectrum of models we could be using to model our time series that go beyond the static. And so the question is, how do we go about choosing these things, and what sorts of test statistics do we use to choose these models, right? That's the crucial question. So just a reminder that from this perspective I mentioned earlier about hypotheses about observables versus hypotheses about parameters, stationarity and non-stationarity, these are terms associated in the statistical sense. These are terms about the parameters. They're not terms about describing what we're observing. They are parameters of our models. And so when something is stationary, we mean that the parameters of our models are not changing, not whether or not we're observing fluctuations. Right? And so if something is very stationary, so it means that if you want to look at how two data points are correlated to each other, then they're completely independent of time. Only the gap between them matters. So that's the essence of when something is fully stationary. And so when we talk about non-stationarity, it means that the covariance structure, the parameters need to actually somehow be dependent on time rather than only being dependent on the lag between them. So from this, revisiting the static model perspective, the standard IID models actually don't capture any correlations between time points in our data. So if you look at our data matrix, the brain, the spatial structure represents the functional connectivity, and there's like non-zero patterns in the spatial structure. But when things are IID, it means every time point is uncorrelated with every other time point. And this covers the static case, okay? And so if you think about the space of all time series models, these IID multivariate normal models, for example, occupy only a small space within them. But there's more general relaxation to this. You can look at models where every time point has some dependent structure with other time points. And so this is exactly what other kind of time series probability models capture. They capture both how do brain regions or voxels depend on each other with the spatial covariance structure, and they model also how every time point is dependent on every other time point using the temporal covariance structure. Okay? And these now you have moved away automatically from IID models. And the interesting thing about this class of models is that if you think about your entire data matrix and vectorize it, what it says is you can completely separate out how the time points are correlated with each other and how the brain regions are correlated with each other. Okay, and so this is how the entire covariance matrix, if you vectorize the entire data matrix and looked at their covariance, would look like. And this is called, when things take this kind of structure, they're called separable, or taking Kronecker product structure. Okay, and these kinds of models, the interesting thing about them is that the spatial covariance structure is not at all changing, but the temporal covariance structure can actually measure autocorrelation, for example, that's changing in time. So how every time point depends on every other time point is allowed to change with time. So this is an interesting kind of non-stationary model that allows for your functional connectivity to be constant, but for dynamics to be changing in an interesting way. And so this is able to capture a very rich class of temporal structure, okay? And there's a lot about this in the time series literature that captures various kinds of non-stationary serial dependence. And so this is an example of saying there's a richer class of models called matrix-varied models. And in a very special case, when you make all the time points uncorrelated with each other, it reduces to the static models. But otherwise, it's a bigger class of models, okay? And one interesting, an important reason why accounting for this kind of serial dependence is important is that if you don't account for it, and here's a simulation to show what's going on. So if I simulate data from a model where time series are serially dependent in this way, and I don't account for this dependence, then I will observe far more false positive connections between brain regions than not. So in red, you see models that account for serial dependence, and in blue, you see the models that don't account for this. And so we're doing a worse job of estimating functional connectivity when you don't account for serial dependence. And there's been a lot more recent results that have highlighted the importance of this issue. Okay, and so another class of models you can look at are autoregressive models, which Giulia already mentioned earlier. One thing I want to point out here is if you look at the full class of general autoregressive models, you instead now have a vector of regions varying across time, and the idea is your data matrix Y is dependent on how the brain looked like at the previous time point, modeled by a transition matrix plus noise. And so your E term, the noise term, captures all the spontaneous non-lagged information. So if I were to say A to 0 entirely, you would get back the IID form, the IID models of functional connectivity. So there's actually two parameters here, both theta and A, that captures non-lagged as well as lagged relationships between brain regions. Okay, so this is an extremely rich class of models for functional connectivity where none of the parameters are changing with time, but they're capturing a lot of interesting features in our data. And so this is another way in which we're going outside the space of the IID class of models to a much larger space of models for time series. But yet, in this case as well, there's nothing that's functional connectivity itself is not changing in time. So in the interest of time, I'm going to skip past some of these, but a lot of this is to show that, for example, you don't need for A to model lagged correlations. You could just use A to model serial dependence. So if A had non-zero off diagonals and just had coefficients in the diagonals, it's modeling serial dependence in time while capturing functional connectivity in the usual way in the green term. In this setting, so what it comes down to is that there's a space of overlap between these two classes of models that I told you. They all meet at both IID models, and then IID models, not just IID, but slightly dependent models. But then they both go off in different directions. And so this is just to give you a sense that even we just considered 3 sets of models for time series across the whole space of time series models out there. And there's an overlapping model space, okay? So it's important to keep this structure in mind as we think about what sorts of hypotheses are we testing about our parameters, okay? Another important class of models that Martin Lindquist and a lot of his colleagues have done a lot with are stochastic volatility models. So volatility models, the essence of them is that it's saying that the variance is changing with time. So if y of t is the time series time point t, it has a variance parameter at time point t. And the variance parameter, sigma at t, is actually dependent both on the time at the previous time point, it's dependent on the observations at the previous time point, as well as the variance at the previous time points, okay? So this is a much richer way of quantifying variability at every brain region or at every voxel. And this class of models also has important consequences because you're now modeling a parameter that's variance that's varying with time. And this has huge impact on what we think functional connectivity is, okay? These are, there's many more models that, again, hidden Markov models, as we mentioned earlier, these are not varying in time, but they model fluctuations, okay? So what is this, where I'm going with this is that I wanted to give you a sense of a rich class of models where there's many other parameters that are not functional connectivity that are all allowed to vary in time. And they all have the capacity to explain fluctuations in the data. And it's important to keep this in mind when you think about testing hypotheses about parameters and testing hypotheses about is functional connectivity itself varying with time. Okay. So coming back to this question about, okay, what are we drawing inferences about? Are we drawing inferences about our observables, or are we drawing inferences about parameters that we don't observe? Okay, so when you want to do inference about observables, this is a thing that is not, maybe an area of statistics that's as widely known, but there's a, drawing inferences about parameters is not the only kind of statistical inference we can do. An important thing is about predicting observable quantities. We can simply ask, how well are we able to predict observable quantities, and try to calibrate our models to do this. Okay, and so a really nice example of this was in Raphael's paper that looked at a bunch of different stationary autoregressive types of null models and looked at how well our observed fluctuations in the data matched a real data set, right? And what you're able to show is you can look at stationary models and produce seeming fluctuations in sliding window correlations. And so what we're really doing here in asking this kind of question is reasoning about observables, right? We're saying what class of models are producing behaviors in the data that we see? And are we using models that mimic the patterns we see in the data, right? We're not saying quite as much about the unknown parameters. What we're really trying to do is make sure our observables match the data, right? And similarly about hidden Markov models, even though they are technically stationary, they're able to produce fluctuations that match the sorts of fluctuations we see in the data. So this is one kind of question that can be asked, right? And so the whole field of statistics that talks about drawing inferences about observables is really predictive inference, okay? And an underutilized thing that we don't yet do here is really ask, well, if we trained our time series models on some data and asked how well are we predicting future observations from that same time point? How well are we predicting future observations? This is a forecasting problem. But we could be completely agnostic to interpreting parameters of the models and just ask, how well are our models predicting brain activity, right? And just say, as long as our models are adequately predicting brain activity in equivalent ways, we can use any of them. And from that mindset, we don't need to be interpreting the parameters of the models at all, right? So I think the key thing that leads to a lot of confusion is the fact that a realization of the data and a function of the data does not necessarily reflect our true unknown parameters. We need to do some additional work to really show that our estimates from our data match and tell us something true about the model. So for example, a hypothesis about parameters in our model could be, is the cross-correlation between two brain regions zero? Is it non-zero and constant, or is it actually changing? Okay, so here's a situation where we've got data that where the cross-correlation between two time series is rho of t, and rho of t is zero, okay? It's uncorrelated and it's not changing in time. And in this paper by Lindquist from a while back, what they did was they used a canonical sliding window approach where we see, fluctuations in time. But this is happening even when two time series are completely uncorrelated and not changing in time, right? But when they use stochastic volatility models to model this data, you're not going to see this anymore. And so this is an example showing that if you think about what sorts of models are appropriate to fit the data a little bit more carefully, and what sorts of models are needed to test this question of, is the correlation zero and is it varying in time or not, you might pick different test statistics, you might pick different ways of estimating the correlation itself that account for other features of the data. That's the other thing here. By accounting for potentially time-varying properties elsewhere in the model, the correlation between brain regions is actually not changing, right? In the same paper, what they also showed was that as you change the window length, which is a thing we already saw earlier, the extent of the fluctuations decrease, but none of them do as well as using stochastic volatility models. In a much more recent paper, what they also showed is that if you don't account for autocorrelation in the data, you will also see much larger sliding window correlations than after accounting for autocorrelations. So roughly speaking, the more autocorrelated your data is even less independent than otherwise. And what this means is you need an even longer window, potentially, to make up for the fact that your time series is dependent. You need an even long window to reduce the noise in the data. And so accounting for autocorrelation, in fact, is also important because you see both the maximum values of the cross-correlations taken as well as the variability of the cross-correlations are much higher if you don't account for autocorrelation than not. So what all of this points out to is that you need to be asking, is there serial correlation in your data? Is that correlation changing in time? Is there time-varying variance? Is your model adequately accounting for that? And it's only after we've accounted for these features in the data that we can let ourselves ask the question of, well, what's happening to the functional connectivity? Is that changing in time? If you try to do that directly without looking at these other parts of the model, it might be that you come to the conclusion that something is changing when it's in fact not, right? That's the thinking about hypotheses about parameters part. And so, how much time do I have?
Around 5-10 minutes.
Okay. So, and a final thing I want to talk about is simulating. So, in order to draw inferences about our parameters, we're using a lot of complicated models. And so, using computational statistics to draw our inferences using the bootstrap is like a very powerful technique to draw and test inferences about our parameters. And roughly speaking, what the bootstrap is, it says, in the real world, there's a whole family of probability models for my data, and I don't know what models are true for my data. I only observe the data, I don't know what the truth is. But I can simulate the bootstrap world, where I take a fit of the model to my data and pretend that that's my true model. And then I come up with a way of simulating data from this observed model. And I use these to generate, pseudo bootstrap data sets. And on the bootstrap data sets, I refit my model many times and draw inferences from these simulated bootstrap statistics. So to take an example, if we take an example of our autoregressive model in the real world, I don't know, I observe y, but I don't know how y is dependent on the previous time points. I don't know beta, this unknown parameter of the autoregressive model. But in the bootstrap world, let's say I fit beta to my, let's say I fit this autoregressive model and have a beta hat. So in the bootstrap world, I can simulate observations y star from this model where I assume that beta hat is actually my true model. And in this context, what I'm really saying, what I'm doing in bootstrapping is I'm saying that I don't know what the discrepancy between beta hat and beta is. But in my simulated world, I can actually find out from my data what's the discrepancy between beta hat star and beta hat, because I know both of these things. I generated one and I fit the other. And so I can use these to quantify, at least approximately, the uncertainty in my data and what the actual empirical variability in my data is. And there's a bunch of theoretical arguments that say that reasoning about this bootstrap world actually tells us something about the real world. Okay, so usually we use the bootstrap to quantify standard errors of our estimated parameters, to quantify confidence intervals, and to do hypothesis testing and generate p-values. So an example of what, I'll get to an example of what that looks like. But this kind of technique is only an approximate technique, okay? We're doing simulations, so if we do only a finite number of bootstraps, it means that there's some simulation error. If I'm wrong in specifying my model, then there's a modeling approximation error, okay? The more assumptions I make about my data and my models, the more I might be making a model approximation error. And then there's the estimation error. If I'm fitting a very complex model to the data, then my beta hat might actually be very far away from the true beta, in which case there's an irreducible estimation error. And so different types of bootstrap do a trade-off between approximation error and estimation error, okay? And so for well-defined parameters, like for example, if we want to test the idea that beta is 0, then we can do a hypothesis test using either a parametric bootstrap or a non-parametric bootstrap, where I effectively I have my observed statistic on my fitted beta, and I have my resampled data sets on which I refit my model and then recompute my test statistics, and I ask how often the bootstrap test statistics are much larger than my observed test statistic, and that gives me a p-value. So, and when the p-value is small enough, I'm able to reject this. So typically the bootstrap has been designed to do this kind of inferences about parameters in your model. And in the context of time series, we actually need to be very careful in how we do these things, but I won't go too much into that detail. But let me ask this question. So let's say I'm going to simulate data from a bootstrap. I'm going to simulate a bootstrap data from an autoregressive model, okay? And what I'm basically saying is I have some data, I fit an A, I fit the theta, and now I'm going to simulate some simulated data from this fitted model. And I'm making an assumption here, which is that all the true parameters are basically my fitted parameters. So here's a question, which is, what does rejection against this null hypothesis that my data comes from this model, what is that really telling us, okay? So is it telling us that if I reject this null model that my data is not autoregressive? Is it telling me that data is not stationary, since vars are stationary models? Is it telling me that the data does not have autoregressive structure specific to this model? Or is it telling me that the data must belong to a more general family of models that include var as a special case? Okay, and here is the poll that is hopefully unlocked now.
It is.
Yeah, okay. So you can go to the audience response and answer what you think, yeah. so these are the options. So you should be seeing that in the response, in the questions being. Sorry? Oh, here? Yeah.
So we have a majority of D here,
Okay.
and a bit of C as well.
Majority of?
D.
Majority of D. Okay. So we'll come back to this question again, okay? So I'm revisiting, we're going to come back. So I'm going to revisit this question that I mentioned earlier, which is, if we've got this increasing, we've got models with increasing complexity, roughly speaking, and there is an overall principle of parsimony, right? We should fit as simple models as we can to the data and no simpler. And so one idea of simplicity here is this weak hierarchy principle I've been alluding to, which is somehow we should account for these simpler aspects of our data and only then proceed to more complex models where potentially something other than the autocorrelation and other than the variance is changing with time. So it's weak because one reason for the complication is that it's not easy to say that all these models are, naturally nested within each other. They're overlapping and very complicated. And this is just this case of like 3. We don't even know what this model overlap structure is for all of these time series models out there. So it's not very easy to test how to proceed in this gradation, but there is like a rough hierarchy. We can say there's a whole class of these, families of these, that might be roughly good enough for our data. All right. This kind of testing one family of models versus another family of models is actually a very interesting problem. There's not a lot of test statistics developed out there to do this kind of thing, unlike the criteria you might be familiar with, like AIC and BIC, to choose how many lags are there in your autoregressive parameters or things like that. So, okay, coming back to this question, what does it mean to reject a specific mark? So if you've got a particular null, var model, and that is now, you've designated that as your null hypothesis, and you successfully reject it. Where in this model space are we? Are we going to be within the autoregressive space? Are we going to be anywhere in this space? Like, where are we, right? We don't know what our alternative is. All we know is that we're no longer in where H naught is, right? So from that perspective, okay, let's revisit this question. Maybe you can get ready to vote again. Same question, what do you think the answer to this is? A, B, C, or D? Are we released?
So now there is more
Yep.
C, actually.
Okay. Okay, that's good. And yes, I did design this for C to be the right answer. So yeah, so if the polls were working, we would see a nice pre-post comparison here.
But people continued answering the first one, so
Okay.
the first one is C as well now.
Okay. All right. Okay. So and again in the paper by Raphael, so he had a nice simulation result where he showed that the kind of var models we simulate, for example, if we simulate only a bivariate var model instead of a multivariate model, then you're going to easily be rejecting the bivariate var model all the time, but you're still in the var model space. You're just in a multivariate var sometimes, right? You could be rejecting on the bivariate and still be in the var space. So there's a nice illustration that, what specific model you're rejecting, we still don't know what that means, right? We need to be careful about model space. So, okay, so here's the final question. Here's 2 data sets, okay? One has, they both have the following, empirical correlation structure, functional connectivity that roughly, the empirical correlations roughly change over time, but this is how they look, 1 and 2, okay? Have you gotten a peek? Okay. So I'm gonna ask, which of these options do you have the most evidence for? First is that both are stationary, come from stationary data sets. Second is that they're both non-stationary. C, there's not enough information to determine if they're stationary or not. D is that one is non-stationary, second is stationary, and E is the opposite. So I'll give you a glimpse of this. If you go to the poll, that should be released now, you'll also be able to see a picture in the poll as well. So give you a few seconds to answer this. Poll still open? The picture? Yeah. All right. So
There is a bit of everything here.
all right. So there's this figure actually comes from this recent paper by Miller, and what they give, it's filled with very nice counterexamples that defy all of your intuitions. Highly encourage you to read it. But what they show is that you can have stationary data that is designed to mirror certain aspects of a real data set, and you could have constructed it such that the data is statistically stationary, and you can do the same way and the data is actually statistically non-stationary. So the right answer is C, which is that there's multiple models that can produce the same structure in our observations, right? And so we can have multiple models that generate same patterns in our observables, and we still can't reason about our parameters of our models. So this means that we need to really think about where our model parameter space is and how we're constructing null hypotheses about parameters or about families of models and so forth to know what it is that rejecting such nulls even mean. So it's a lot easier to reason about observables, and it's very difficult, hopefully, taken away from this, it's very difficult to reason about our unobservables. And so choose your inferences carefully, okay? And the key thing is, what we should really care about is, the key thing to care about is, are we explaining fluctuations in our data? I think it's an interesting question to ask, are our parameters non-stationary or not? Are the parameters themselves changing? But we don't really need functional connectivity itself to be changing. It might not be, right? It might be something else that's changing. And in terms of work that needs to be done, there's a lot of known unknowns here. We don't still know, what are all the different time series models out there? What are all compatible and are roughly equivalent, or which are the ones that are all good enough, or good enough for what purpose? And you'll get some insight into that in all the other talks later today. Want to give a shout out to this Women in Science repository. And if you like my talk, you can go look me up there. If you have any Q&A, I encourage you to ask Q&A so that as the other speakers go on, and we can have some interesting discussions. That's it.
Thank you. So we have time for a few quick questions.
I figured we can have time for questions, but yes.
No, but Vince is stuck outside of the room, so the time comes. There is Vince.
I checked it in the speaker, but I didn't check it.
Because you might need to plug in your computer there. This room is too small.
It is, yeah. Oh, they're doing something. What's that?
I gotta go run and get the line.
Oh, okay. Are they going to bring mine up? Who's the... I guess he's back there. I'll tell.
Okay, so next speaker is Vince Calhoun, who has done some pioneering and seminal work in time-varying functional connectivity, and who is now with the Mind Research Network at UNAM. So,
I switched.
Vince? You are at Yale now, or
I know. I'm in Georgia. So.
Georgia? Okay, sorry, I saw
Surprise.
Yale as well. Okay, so Vince.
Actually, just last week. So yeah.
Okay.
All right. Thank you. So I'm going to go through a number of different topics, introducing some more of a data-driven type approach to analyze connectivity, and then highlight some clinical applications that we've used. So the basic approach that we like to use is basically to do an ICA decomposition and then take component time courses. And then from there, those are sort of our time courses, and then we basically can do a straightforward sort of sliding window type approach, which you've heard about earlier, which you can then compute from that time series. You can do clustering to get what we're calling states, which are sort of patterns of connectivity that are transient, that individuals are moving closer to or further away from over time. And so for any given individual, you get a state vector like this, which sort of is an estimate of which of these states they're in at any point in time. Okay, and again, the idea is to model the data so that we don't assume this is all one thing, but to capture variable connectivity over time. And in some early work, we applied this to look at schizophrenia versus healthy controls. And so what you see here are 5 different states. This is resting state fMRI data for healthy controls and schizophrenia patients. And then each individual state is contrasted. And a couple things to notice are that the differences tend to be different, right, in each state. So we get sort of, this sort of thalamic sensory motor correlation kind of clustered into state 2 and 3. Beyond that, we get metrics that we can compute on each of these states. So for example, you can compute the mean dwell time, which is the average amount of time they spend in any given state once they enter it. And then you can do statistics to compare the groups. So here we have a comparison of healthy control schizophrenia patients, and they spend significantly more time, the healthy controls do, in these more modular states 1 and 2. The patients spend significantly more time in these sort of weaker, less modular states 4 and 5. So it kind of changes our interpretation a little bit in that in schizophrenia, it's not sort of a global decrease in connectivity, it's actually transient decrease, and it's not actually completely, this isn't completely flat, right? So it's changing which regions are sort of connected over different points in time. So that gives you sort of an example of why this could be a useful way to look at the data and kind of opens it up a little bit. Instead of assuming that each individual's at one state at any point in time, we can also do things like treat it as a state space. So here we have state 1 versus state 2, and there's sort of a what we've got is we've quantized the levels here, but you can also treat it as continuous. And essentially, one individual might start here and then move here, here, and here over time. Another one might just go back and forth like this. And then we can represent each point on this grid in something we call a metastate. And so if there's 2 states, there's 2 numbers in that vector. If there's 3 states, there'd be 3 numbers in there, and it tells you the level that they're in each state at any point in time. And then we can compute statistics on these metastates, which are more global measures that tell you about what's going on in the dynamics overall. For example, the total distance traveled, the number of distinct metastates, et cetera. When we look at that same schizophrenia data, we found almost, across the board, everything here is negative, in that there's diminished dynamic fluidity and diminished dynamic range in the patients. And importantly, if you look at how we get the states, we can do k-means clustering or PCA or spatial ICA or temporal ICA. Regardless of that, we actually got consistent directionality, right, for the patient. So for the global measure, if you look at the individual states, they look very different. PCA gives you very different states than does ICA. But at the global level, they're much more consistent. And we can also do interesting things like compute what we call a hub state, which is essentially a state where when you get in there, you spend significantly more time than in the other states. It's kind of like a sticky state. Think of it that way. And what we find is schizophrenia patients exhibit many more hub states, and their time in those states is correlated with their negative symptoms. So again, it gives you sort of an intuition that makes a little bit of sense. Another thing I'll sort of touch on a little bit more later is that we're talking about connectivity, which obviously is correlation over time, but you can also look at dynamics in the activity, right? One time course as opposed to correlations between pairs of time courses. And there's been a number of papers, I think, that have looked at the relationship between the activity and the connectivity dynamics. And in some cases they're similar, in some cases they diverge. And actually those cases are all interesting. Here's an example where we simply computed an ALF measure on an individual time course, so amplitude of low frequency fluctuation, in a windowed manner. And so we have basically windowed ALF, and then we have windowed dynamic connectivity, and then we look at where those things are similar and where they're different. And these are sort of windowed ALF states, and these are dynamic connectivity states. Okay, so validation is obviously important. A few things that we've looked at are just replicability. Is there some canonicity? Are these things recurring in different data sets? And so we took a data set of 7,000 subjects collected at the Mind Research Network and split them into 28 subsets, independent subsets, and ran our pipeline on each of those separately and then compared them. And we found that about correlation in the, I think we estimated a number of different states in them. Correlations were ranging between 0.7 and 0.8 in terms of those patterns that came out. So they were actually replicating pretty well. And also the amount of time they spend in the state that they spent the most time in was consistent and replicated across the data sets. And also, if we look at more explicitly dynamic metrics, so like the metastate measures I mentioned earlier, here you can see the distribution of those 4 different parameters across those 28 different data sets. If we disrupt the ordering of the time courses, it very clearly destroys those dynamic metrics, as you would expect.
Can you repeat the definition of state? I'm sorry.
So a state is basically if you take a time series of connectivity matrices, so they're changing over time, and then you cluster those, you basically, the centroid of that cluster is what I'm calling a state. So it's essentially a pattern of connectivity that we estimated from the data that these matrices are moving closer to and further away from. You can think of it as like a pattern of connectivity that recurs transiently over time. Another way to try to validate is to look at multimodal information, so concurrent EEG data. And so here what we did was we used alpha power and delta theta power, and we basically ordered the states from left to right in terms of sort of drowsiness measures. And you can see for the least drowsy here, we have more anti-correlation with default mode, and then when it gets to the far right, you see sort of hyper synchronization, right? Using some data from Enzo Tagliazucci's group, where they have long data that was sleep staged, concurrent EEG fMRI, we looked at classifying sleep state and using an ICA decomposition, as I mentioned before. And here I show you an example of one of the hypnograms and one of the state vectors. And so we do a pretty good job of classifying sleep state. We can get an average of about 70 to 75% accuracy using k-means. We also tried the dynamic correlation coefficient, which is sort of an adaptive window approach, which also was able to classify, but not quite as well. Another question that we asked was how consistently can we classify states in the wakeful condition only? So the most wakeful condition, are they fluctuating? And here we were getting a fairly high accuracy fairly consistent for sort of states within the wakeful condition were estimated consistently. That doesn't mean there's not degrees of drowsiness within wake, but it could also imply that there's obviously variation in other, there's lots of things that are changing during resting fMRI. These dynamics are also highly task dependent. So this is some data from Peter Bandettini's group. And they basically have 4 blocked tasks, and if we run our pipeline on that data, we basically get each task as a separate state, right? So it's driving a lot of the variability. If you just look within one task, then you start to see substates within that task. But again, it's levels of variability here. Task is probably the biggest driver, drowsiness, and then under drowsiness is you know, probably the most interesting variation, but very small changes, right? Dynamic connectivity we have found in most cases to be more predictive than static connectivity when you're looking at clinical groups. And so here's a direct comparison where we have sort of static connectivity in a 3-way classification, bipolar, schizophrenia, healthy controls. About 60% for static, jumps to about 84% for dynamic, and 90% for combined. And this makes sense because there is a lot of variability at rest, and we want to, you know, with the states, we can sort of try to characterize that as different states. Accuracy is always higher with more than one state, at least in what we've looked at. So here's static analysis. This is, again, just a 2-class comparison, schizophrenia, healthy controls. And this is 2, 3, 4, 5, et cetera, number of states. And you can see the classification jumps substantially from 1 to 2 or more. Beyond that, if we say, well, maybe not all of the states are informative about diagnosis, right? Maybe a subset of them. And so if we use a brute force method to try to do feature selection and select states that are most informative, we see that, you know, here I've got single, static. These are all dynamic. These are using the feature selection approach I mentioned, and we actually do substantially better if there's a subset of the states that we actually end up selecting for classification. One example here where we've looked at mild traumatic brain injury, we find classification here with diffusion data was about 66%, resting fMRI static was about 78%, and dynamic or time resolved is 92%, and we also find that the most informative regions were sort of long distance connections between sort of motor cortex and cerebellum. Excuse me. And this isn't limited to clinical groups. It's also limited. It's also exhibited in cognitive scores. So this is some work from Lucina Uden's group and Jason Nomi, and they've basically looked at executive function in human connectome data, and they found a replication in terms of how, for example, one of the states was fit to executive function consistently across 2 different independent subsets on that data. Okay, and you've heard a little bit about null models, and I just sort of wanted to make a couple points. One of which is that there's a spectrum, right? So we can talk about stationary and non-stationary, but those 2 measures are sort of extreme and probably less useful for what we're doing in the brain data. We can look at sort of stationary constrained, and we can look at real data here. So this is sort of spectrally constrained data. And we can also do something like epicless, right? So you basically look at a time, you try to minimize the variation over time in a simulation, as opposed to simulating it at the population level. And you can compute different measures to try to sort of statistically compare these things. The earlier speaker mentioned kurtosis as one measure. Kurtosis is very good at detecting outliers. It's not very good at detecting subtle changes in connectivity. Another approach we've been working on is called it's a wavelet-based approach called multivariate phi, still in development, but is doing a pretty good job at sort of detecting and differentiating these 4 cases. terms of clinical applications, we've got the first one here is just to look at more subtle and more interesting comparisons along the mood and psychosis dimension. So we've got schizophrenia, schizoaffective disorder, bipolar disorder, and healthy controls. And what we find, for example, in one of the states, you can see that there's quite visually different configurations in terms of these 4 groups. And they're statistically different as well. Attention deficit hyperactivity disorder also shows differences in dynamism. Interestingly, though, you get slightly different answers if you look at different scales. So if you look at sort of the global level across all of the networks, you find increased dynamism. And if you zoom in just on, say, default mode network, and so you have multiple nodes within the default mode network, you see the reverse pattern. So I think there's a lot of interesting things that we still don't know yet in terms of which scale we should be looking at and what that's telling us. We've also looked at autism and have found reduced dynamism in autism, which you can see here, sort of a comparison of percent occurrence. And the autism folks tend to spend the most time here in this state, and controls are in this state here. And then we see also correlation with clinical scores as well. And here's another example looking at Alzheimer's and subgroups. So we have a sort of a vascular dementia group and a cognitive group and an Alzheimer's group. We see that when we look at the resting data, that state 3 is able to differentiate, for example, those two patient groups from one another. And I think the last sort of global example is the substance use data set. So here we've got people taking different substances, either smoking alcohol, combined alcohol and smoking, marijuana, combinations, et cetera. And again, the dynamic, and I know I'm glossing over this. Just here like that. Okay. Glossing over this a little bit, but we are, I'm sort of trying to just illustrate some examples where we've looked at dynamic connectivity and found it to be relatively informative in terms of just differentiating these groups. And so smokers, for example, you can see are predominantly here in state 1 and state 5. And this is sort of a summary of some of the findings we've looked at the meta-state level across a number of different disorders, and we're seeing some evidence of hints, I guess, of specificity across disorders when we look at these states. There's some similarities. For example, you see a lot of these groups have reduced numbers of states, right? So these first, many have reduced numbers of states. But if you look at the 4 patterns, actually they're somewhat distinctive across all of these different groups. So in this section, I wanted to touch on other metrics that you can use, other ways of measuring dynamic connectivity, again with more of a data-driven flavor. So instead of just looking at the time series and looking at correlations, you can look at sort of jointly at the frequency distribution and at the phase. So are they lagged or leading on from one another? And you can do this with a wavelet-based approach. And so here the color in each one of these is a state, and the state actually contains the amplitude, which is the strength of the color, the phase, which is the color itself. So here you can see these are in phase and these are completely out of phase, and the frequency distribution here. And this lets you separate things that might have similar amplitude patterns but different frequency fluctuation patterns. There was some talk earlier about windows and how do you choose the windows, and you can use fixed windows, adaptive windows, et cetera, if you're using a sliding window approach. Here is one that's simply just windowless, so it's using a dictionary learning approach to estimate directly from the data. And so this is an example of a decomposition approach that doesn't care about the ordering of the time series, right? It's just going to identify patterns of connectivity, even if they immediately transition with no delay or change. And so then if you have here our approach versus a sliding window approach on actual sort of data that's ordered versus shuffled, you can see this is preserved. Right? Another way to deal with windows is to look across, is to think about it in the context of a frequency bank, right? So what a window is really a sort of a filter on the connectivity, right? That varies over time. And so we can just simply build a filter bank which captures all possible window sizes, right? Essentially, from small to large. And so then what we get out of that is we get states here, and then we get the weights for each of the filter banks from low frequency to high frequency, right? And so if it's exhibiting sort of a high value on the left, that means it's kind of static. It's not moving very rapidly. If it has a high value on the right, then it's much more transient, right? It's probably going to be missed if you have big windows, right? And then you have some that are sort of broadband in between. And so this is an approach, I think, that can be pretty useful because you then don't have to commit yourself to one window or do your analysis you like and get some cool results, and then the reviewer says, what if you change the window size? And then you go and you change the window size and the results look different, right? And then you're like, oh no. So this at least gives you a way to kind of look broadly across all of those all at once. Another way to look at this is sort of with trajectories. And so here, for example, if you compute, this is just a measure of energy. So things that sort of are clustered together will tend to have a high energy. And so then we're looking essentially at pairs of time courses on a two-dimensional plot relative to one another. And so we get these little clusters that have sort of higher energy, and then they have a representation in terms of what they look like in their patterns of connectivity. And another one that we've been looking at recently is instead of just taking the time series and clustering those, we can use the temporal derivative. So this is just sort of the first step forward. So we have the temporal derivative, and then we have the original time series. And so then we get a pair at each, a cluster has a pair where this is the connectivity for the main time series, and this is the connectivity for the derivative, right? And the derivative tells us whether the information is flowing into or out of the state itself, which gives us a little more information about modeling, right? So then if we want to, we can think of, for example, here we've got two pairs of clusters that are fairly similar to one another, but the directionality is opposite in the derivative. And then we can start to think about things like, oscillations in and out of a state or attractors, right? And so we're kind of coming at it backwards, right, from a data-driven side. And one cool example we just looked at was, again, looking at traumatic brain injury, where we find these sort of healthy brain attractors, that are shown right here, which kind of break. So those derivative patterns change substantially immediately following injury, and then they start to recover, and then they fully recover after 3 to 4 months following the injury. And again, there was mention earlier about sort of spatial and temporal, and I think that is something that's kind of been overlooked or sort of not really discussed a whole lot in the field yet. But you can have fixed regions that vary depending on the time point that you're in terms of their distributions. You can have regions that vary in space, but their temporal relationship stays the same. And you can have regions that vary in both, right? And so these have not been, in particular, this one here has not been well studied at all. And it's been largely sort of ignored or not discussed much. So I think we need to do a lot more work in this. A couple ways to get at that are, to think of, well, let's break our data into a small number, into a large number of spatial basis functions and look at how they combine variably over time, okay? So this is some work from Arman Araji in my group, and so here you can see within each domain we get some dynamics over time that consist of variable combinations of, well, let's just look at this middle one, of these 5 different sort of basis, spatial basis functions, right? So that's still kind of assuming that the spatial basis functions are fixed, right? But at least you get some variability at the larger network level. You can also go completely just voxel-wise and spatially fluid. And so here we're looking at estimating networks at each time point, and we get a voxel-wise map at each time point. And then we can see if the network sort of flows and connects or separates from other networks spatially. And so here, spatial white means it's sort of always connected between 3 spatial states. And then these different colors tell you which state it sort of tends to fall in most consistently over time, or sort of always blue, which means always combined between state 1, overlapping between state 1 and 2. And this is also going to require us to develop some new metrics, right? So here, for example, we're trying to compare, for example, 2 different states where some of the voxels change, 2 different time points where some of the voxels change, and so we use a spatial distribution, sort of binning type approach here to get a metric out that we can then analyze in the same way that we do the temporal dynamics, like dwell time and things like that. Okay, and then I'd like to throw in sort of at the end a couple more crazy things, which is here we've got trying to combine genetics or genomics data with dynamic connectivity data. This is a schizophrenia study, and I like this one because this is that example I showed you before where, remember, the healthy controls spent most of their time in state 1 and 2, or the modular state. And what we found was that we're using something called parallel ICA. We're getting out this pattern of single nucleotide polymorphism data that we can then compute a schizophrenia risk score from using psychiatric genomics consortia data where they had hundreds of thousands of individuals. And what we find is that the correlation between the SNP pattern, which was showing a risk for schizophrenia, was lower. The lower the correlation between state 1 and the risk score, the more at risk you were, or the lower the correlation between the SNP score and the state 1, the more at risk you were for schizophrenia. And so this link between, patients spending less time in state 1 is also reflected in a link between the genomic data and state 1 as well. Okay? And that the details are fleshed out in this paper here. Okay? And then the last example is trying to combine brain structure and brain function. And so here we're using a deep learning model where we combine something called an attentional model, where you have a figure and a caption, and you want to highlight a word in the caption and see where in the figure is relevant. Right? Here's another example where you've got girl and it highlights the girl's face. Okay? This is an alignment model used for translation, and that's a sort of a sequence-sensitive model. So we're asking maybe one word maps to 2, or the ordering of the word changes over time. And so if we combine those 2 models together, we have essentially the structural information, say gray matter segmentation. We do ICA on that to get covariing patterns of gray matter. And those are our figure, that's our figural information. And then here on the right, the dynamic connectivity, the state vector here is kind of like our caption, right? So we have dynamic information and we have the static information. And then we create a model here where we've got essentially the dynamic information, the sequence predictor, the structural static information, and the attentional network, okay? And when we look at those together, we find evidence of substantial alignment between structure and function. So here, for example, state 3, again in that same schizophrenia data set, is aligned with this middle temporal gyrus, structural region. And that also correlates with their cognitive score. Okay. All right, so in the last, and so we've released all of our tools that I mentioned earlier in terms of the dynamic connectivity and the time frequency analysis and the windowless analysis and et cetera are all contained within the dynamic connectivity toolbox that's part of the GIFT software. And just a few screenshots because we're not doing demos today, but here's an example of kind of some of the some screenshots from that and some of the output that you get from that tool, and you can get it from this website. And then thanks to my lab and colleagues, and I guess we've got a few minutes for some questions.
Sure.
Yeah. Okay. Yeah. Thank you. Yes, you first. Yeah.
So sometimes I was reading one of your papers on the steps, and I think I vaguely remember that I was thinking it's somehow the text of the author to choose the number of states that wants to be used. So how do you deal with this?
Yeah, and that's asked quite a lot. So there are. In any method you use, there are parameters you've got to pick, right? And so one of them we've talked about was the size of the window. Another one is if you're doing a state type analysis, you have to pick how many states there are. And so we can estimate that from the data, using like AIC or MDL type approaches, which is what people will often do. But you'll often get reviewers that say, well, I want to see what happens if you pick 4 or 6 or 7, right? And so you'll see, like in the supplemental material, we often have kind of 2, 3, 4, 5, 6, 7. So we look at a range of them. It's a free parameter, and so it is something you have to pick. And I would encourage you to look to make sure your results aren't super sensitive to just that one particular choice. Really, what it's doing is it's splitting the data into smaller or larger pieces. So yeah. Yeah. Mm-hmm.
I kind of feel that variance explains low to from high, and also that's the first question. And the second is that it shows only 4,000 steps, and I wonder why, because there's a lot more.
Yeah. So we applied a threshold, a p-value threshold to the PGC data to reduce the number of SNPs down, so that we didn't have too much of a dimensionality challenge when we were analyzing this, right? Because we only had about 300 or so subjects here, and so we didn't want to have too many SNPs to analyze. And in terms of the, it was interesting that we found that correlation. I thought we did look at a different data set, and we see a correlation as well in that one. So it gives us some confidence that that it's real. I don't know if that the final answer will be that strong. We'll kind of see what happens, but. I found it quite interesting. So, yeah. Mm-hmm.
And I think it might be just because the reason you're choosing the top SNPs. So you're looking more at the sort of brain expression focus.
Yeah.
So you're using more of that.
Right. Could be. Yeah. You're welcome. Any other questions? Someone's going to say, "Where are the chairs? I want more chairs." No. Sure. So there's a lot of ways to do that. So the question is, how do you align states, right? So if you do completely, as I mentioned, completely separate analyses, you might get things that are not quite the same. In that replication study we basically did it like a greedy match. We did correlation and we ordered them in a way that was similar. Maybe you won't find perfect matches. Another thing that we've done is if you've kind of got, we'll call it a discovery data set, and you analyze a large data set and you get states and you like those, you can go to a new data set and you can initialize the clusters using those states to get yourself in the ballpark, and then you run the clustering from that point forward. So now you have some alignment that you've imposed sort of as a prior. That's another way to do it. So you can kind of do it up front, you can do it after the fact. You can also put everybody in the same analysis, you know, and that gives you, that's a little bit more constraining, but it still gives you, you know, that gives you more of an alignment between them. So, yeah.
Yeah, thank you for the talk. I found it really interesting. Especially the part about the differences in the state dynamics between controls and patients.
Mm-hmm.
And I was just wondering, because a lot of results were on group level, is there any kind of, so what is the kind of individual
Yeah.
diagnostic value of this?
Yeah,
like
good question.
predictive
Mm-hmm.
value of this? Is there, have you?
Yeah, we've looked at that. So the paper where I show, or the result I showed, the bipolar schizophrenia healthy control classification result, that was single subject, and so we're going to each subject and estimating state information, and it was predictive. So anything in here that I talk about classification was cross-validated out of sample classification. So that was trying to get at that. I think that question you were asking is, yeah. How are we doing on time, Lurie?
Yeah, I think we will thank Vince again. Yes.
Yeah. Okay.
Okay, so we will get started with the second part of the course. So the first speaker for the second part is Shella Keilholz from Emory University, and Shella is gonna talk about the neural basis, so how we can relate these fluctuations that we see at the macro scale, how we can relate these fluctuations to the neural level and the neural dynamics. So Shella.
All right, thank you for giving me the chance to be part of this very cool course. So I'm gonna start off, if I can get my slides to move, there we go. I'm gonna start off with an example that I think motivates why we're interested in looking at the neural basis of this time-varying connectivity. So this will seem very naive to you all after looking at the sophisticated techniques that were described earlier in the course today. But this is from, you know, gosh, close to 10 years ago now, when we were first starting to look at dynamic connectivity. And so my lab works a lot with anesthetized rats, and we were looking at connectivity between left and right S1, and you had strong connectivity, but we know that S1, the primary somatosensory area, is also connected to the secondary somatosensory area, S2. And so we wanted to know why they didn't show up as correlated. Seemed kind of weird. And one of our ideas was maybe that they're only correlated part of the time, you know, so that they're kind of doing different things. They're not constantly in communication. And so I've got an example over here. See, I don't know if you can see my cursor. Probably not. Okay, so the example over on the left shows sliding window correlation between left S2 and left S1, which don't show up as strongly correlated when you do the average measure. And you can see that there are times when it's high and times when it's low. And the different colors represent different window lengths that we used. So we saw this and we said, wow, that's exciting. There's all sorts of interesting things going on. And we got really kind of thrilled about it all until we did a control analysis. And our control analysis was to take the time course from S1 from one rat and the time course from S2 from a different rat that didn't have any shared temporal information. And it looked exactly the same. So if you look, these are just two histograms of how long each pair of areas spend in a high period of correlation, low period, or middle. And what you can see is that the random and the S1, S2 connection look exactly the same. So just by the properties of the signal, we're getting something that looks like changing correlation. So that really motivated us to go in and to try to see what we could detect that might be actually linked to some of these features so that we could know better which ones might have real meaning and which ones are spurious. So I guess if you're talking about a neural basis for time-varying connectivity, your first question is, well, is there a neural basis for average functional connectivity? I didn't make polls for this course because most of my answers are either all of the above, none of the above, or we don't know. So there's not really any good straightforward questions for the most part. But this is one. Yes, there's a neural basis for functional connectivity. I'm not going to go into that now, but there are many, many studies out there that show that these measures of correlation tell you something about the underlying neural network. So we've got some with EEG and MEG in humans. We've got some looking at ECOG separately from fMRI that gives the same sort of structure, again in humans. We've got sessions from the non-human primate where you could actually record from an electrode and measure fMRI, and then a lot of the work in rats where we can do the microelectrode recording in fMRI as well from different sites. So I think at this point there's a pretty good consensus that there is something meaningful in these average measures of functional connectivity. And so, if you think there's a relationship between average functional connectivity and average neural correlation, it makes sense that there ought to be one for time-varying correlation as well. So we went to explore that a little bit more in detail. So this is the question I was asked to address for this talk, and I wanted to change it a little bit because I think the right question is really, is there more than one neural basis for time-varying connectivity? There are a lot of different things going on in the brain. There are a lot of different dynamic methods we can use to look at it. And I wonder if maybe we can use some different methods to separate out different aspects of what the brain is actually doing. So this is just to kind of give you the framework. If you look at brain activity, if you do recordings, there are a lot of different ways you can do it. And they range from looking at things that may be even common to the whole brain using EEG, or very largely distributed where you can get large-scale oscillations. Things like alpha oscillations have been closer. Is this better? Okay, tell me if you guys can't hear me. I tried. Oh, there it goes. Okay. Ooh. Got to watch out for us short people. Okay, so EEG, very wide range signal, right? Lots of information, but hard to get spatial localization out of it. Going to animal work especially, we can look at things like local field potentials. So these are potentials that we get from groups of neurons, things that are kind of working together in a coordinated way. You might think of them at the column or layer level, for example. Spikes, the activity of a single neuron. So very localized and very fast. And then finally, membrane potentials, where you can actually look at changes at the level of a piece of a cell even. So all of these are well known. So there's this range then of spatial and temporal scale in both the brain activity that we can measure and then the methods that we can use to look at it. So on the spatial scale, we've got things that are global, like the whole brain EEG, and then looking all the way down to the synapse level. So still having... Still nearer. I hear feedback. Okay. Is this okay? Okay. It's just kind of ringing. Okay, so then in terms of the temporal scales, we have things that go very fast. I put it approximately 1,000 hertz because action potentials are on the scale of a millisecond. And then we have things that are very slow. And up at the top, I put seconds to minutes because those are scales that are relevant for fMRI. You can even think of much longer scales, right? At the ultimate extreme is the scale of the lifespan. Our brains change as we grow and age. Okay, so the dynamics that we've talked about so far in this course also have different spatial and temporal scales. You can think of dynamics of the global signal. There's something that I'm going to talk about in a bit called repeated spatiotemporal patterns that we haven't really discussed so far. There are these sliding window correlations between areas and the sliding window correlation matrices that we cluster into brain states that give us information about how the whole brain might be changing. And then there are these coactivation patterns in individual events that also contribute. So I think my question is, if we look at different aspects of this, can we maybe get a clue as to some of the different features of the brain's activity? So I'm going to start with global signal. So if you guys have sat in any talks on resting state fMRI so far, you know that global signal regression is very contentious. And part of the reason is that there's a lot of noise in the global signal. Anytime there's head motion, it impacts the global signal. Physiological noise is very present in the global signal. All of these things are these nuisance variables that we really don't want to look at if we're trying to look at brain activity. On the other hand, there's also some sort of neural component to the global signal. And one of the earliest papers that really examined this was from Scholvink et al., where they took the signal from an electrode in a monkey and looked at how it correlated with the MRI signal through the rest of the brain. And they saw a very widespread correlation at approximately the time of the hemodynamic delay, which suggests that there might be something neural underlying these global fluctuations. So since then, or kind of in parallel with that, there's been a lot of work looking at other links of the global signal to, say, EEG, for example, or to vigilance levels. So I would point you especially to the work of Wong et al. In Tom Liu's lab, where they've looked at how caffeine affects global signal changes and vigilance and how those are all related together. But just to give you an example, shown on the bottom there, they've plotted the change in vigilance before and after caffeine versus the change in the global signal amplitude, and they line up very nicely. So if the global signal is related to vigilance, it seems like there must be something neural there. This is really my favorite study of the global signal. It comes from Garth Thompson and Famid Haider's lab. And what he did is looked at the PET signal along with fMRI in eyes open and eyes closed conditions. And when you go from eyes closed to eyes open in PET, you get this shift in metabolism that changes kind of the background of the metabolic signal. And that shift in metabolism is linked with a shift in the global signal from MRI. However, they didn't see changes in the variance measures of resting state fMRI. So that kind of suggests that global signal is reflecting maybe this baseline shift, which is really intriguing, I think. Just a couple of more very preliminary studies. One at the bottom left is from my lab, where we looked at the coherence between 6 widely spread electrodes in the rat. And this is only LFP, no MRI data. But you see that there's very strong coherence in the frequencies below about 10 hertz, again, suggesting that there's some common neural signal across the whole brain. And then again, we looked at the fMRI signal, the global signal, and what we found is that it's not really so global after all. So I'm going to continue using the term global signal very loosely, but it may imply that certain networks contribute more, certainly that cortex contributes more, and it depends on exactly how you do the normalization, how much different areas contribute. So we did see, and this is now at the bottom right, that certain areas had a stronger contribution to the global signal than other areas do. So there's something kind of specific about it, but not completely. And it lines up really nicely with the areas that show the biggest changes between eyes open and eyes closed in PET. So again, suggesting that maybe this metabolic shift is the basis for global signal. So the upshot is we think that the global signal does have some neural information, possibly these baseline shifts in metabolism. There's going to be a symposium on Tuesday called, the Global Signal Strikes Back, I think. So I encourage you to come to that if you're interested in learning more. Okay, so I'm going to move on to something that people haven't really talked about yet, which is spatiotemporal patterns. We call them quasi-periodic patterns. It's something that my lab has been very interested in for a while. Ever since that we found you can take a resting state fMRI signal and find a repeated pattern of activation and deactivation along major networks that follows a very stereotypical path. It's kind of like if you were thinking of the brain as a complex system, it seems like this might be the limit cycle, a path that it's trying to follow not quite continuously, but very frequently in the background. So we have an algorithm that identifies this chunk of 3D by time data, so 4D, a volumetric pattern over time. Time period's about 20 seconds. And the algorithm also puts out this vector that tells us when that pattern is strongest in the data. So that's what we're going to be looking at. This is what it looks like. This is an HCP data. Let me see if I can get it to play. So right now you can see that the DMN is deactivated, so the blue shows colors below its average level, the red shows colors above its average level. And when I play this, oh, tell me it's going to play. When I play this, is there any way you can press it from behind? It's embedded. It shows up at this speaker ready room. No? Alas. Oh, there it is, okay. Okay, great. So, well, it tried. Okay, well, I'll just tell you, I'll tell you what, I'll just tell you, and you guys are welcome to look them up afterwards. It's in many of our papers, and we have a poster on this here as well. Anyway, the activation in the task positive network and the deactivation in the DMN are going to swap in a very stereotyped way with propagation along the cortex in between. At the same time, over in the cerebellum and in the subcortex, you're going to see the same patterns that the areas of the cerebellum that are most connected with the DMN light up at the same time as the DMN. The ones that are most connected with the TPN light up at the same time as the TPN, etc. So anyway, you'll just have to take my word for it. I don't think the computer likes it today. So we found these patterns, and we wanted to know what they were. We were trying to understand, what these might be, so we wanted to look for a neural basis. And we started off by doing some simultaneous microelectrode recording and fMRI in the rat. So I'm sure you guys have probably seen some of this before. We have to put electrodes into the rat brain, which tends to mess up your MR image. The one at the top is one of our first attempts. You see the big signal loss where our electrode is. The one at the bottom is one of our later attempts. We actually have electrodes in both sides of the cortex. But the image looks pretty good. I think you'll agree. We also have to do some cleanup on the recording because when you look at the LFPs, every time we acquire the image, it saturates the amplifiers because the changing magnetic fields introduce a current. And so we had to get rid of that so we can clean up the LFPs in between. But when we did all of that, we looked at the coherence between the MRI signal and the LFP signal. And because we didn't really know any better at the time, we looked at the coherence in really slow frequencies. And electrophysiologists will tell you they don't usually use those frequencies because there's a lot of drift and other noise. So they usually just start at 1 hertz. But we looked below because we didn't know not to, and we found that actually in our setup, in our very noise-free environment in the Faraday cage and everything, we get very nice coherence between our MRI signal and these very slow electrical oscillations. And you can see the coherence plotted over on the right. The shape of the coherence itself changes depending on the anesthetic you use, which we think is probably related to both neural and vascular effects. But there is significant coherence in both anesthetics. So that's fine, that's nice. That gives us another kind of average suggestion of a neural basis for functional connectivity. Getting back to dynamics, we looked at how the pattern of correlation changed over time. So I want you to look especially at the dexmedetomidine data because it's easier to see there. That's at the bottom left. You'll see that if we change the time lag between the MRI signal and the LFP signal, we get the standard positive correlation at about 2 or 2.5 seconds, which is the hemodynamic delay. And then we get negative correlation at around 5 seconds. And that was very reminiscent of what that quasi-periodic pattern looked like in the rat. We'd have activation and the deactivation of these somatosensory areas. So we went on. This is another movie that is almost certainly not going to play based on the experience with the last one. But I'll tell you, again, I have this in the Thompson paper, describe the Pan one, and then there's a Thompson one that shows that if you do play these, the template that we get from just the MRI data looks just like the template, just like the data we get when we do time lag correlation between LFP and bulk, which suggests our template in the MRI data is pulling out this propagation pattern of infraslow electrical activity. So we've also looked at this in humans. It's a little bit trickier with EEG. Getting those low frequencies is a little bit harder, but we were able to pull out something that showed kind of the same alternation. It's not the whole brain network, but we can get this alternation between correlation with the somatosensory and motor regions, and then the same kind of the inversion of the same ones at about half of the hemodynamic delay again later, suggesting again that this infraslow basis for these patterns holds true even in humans. So the problem is that we've tied this now to these really slow electrical activity patterns, but nobody really knows where those are coming from either. So now we have two things that we don't understand. looking at the pattern of propagation in the QPPs, what we found is that if you plot the number of voxels that activate at each point of the pattern, the ones over by the LPC peak, that's indicated by the line at the right. So if we look at the things that peak the earliest, they tend to be in the thalamus and in the deep brain. And so that suggests that maybe these are involved in kind of the initiation of the pattern. So that's one clue. Another clue that we found is that if you look at functional connectivity gradients, so these are the gradients plotted by Daniel Margulis et al. In the 2016 paper, where you take functional connectivity with all voxels and then kind of reduce the dimensionality to get the primary directions of functional connectivity gradients. So he's got 5 I'm showing over here that are plotted. If you look at the quasi-periodic pattern that I showed you, it lines up really nicely with the first one, and our patterns sweep across those gradients from one end of the gradient to the other. So that's maybe another clue. There's something going on there. So trying to figure out where these are coming from then, we had a couple of ideas. One is that we know the brain has this structural network, right? So you can take the brain, you can divide it up, you can calculate correlation between each parcel, or you can calculate diffusion tensor tractography between each pair of parcels and get some sort of structural framework. If you have a network like that, it's possible that it might have some sort of resonance, or some sort of self-organization. So we thought that was one possibility. The other possibility is that in deep brain areas, there are things like the locus coeruleus that have very widespread and pattern projections. And we thought maybe that's another thing that could be involved in driving these patterns. So just a few words about the first approach first, because I know that Michael will be giving you a much better overview of this in the next talk. So we make our brain network model using structural connectivity on a parcellated brain. At each of the parcels, we drive it with a differential equation chosen from different neural mass models. We let that run. It gives us simulated data. And then we did our QPP analysis on it to see what we got out. So I'm showing the QPP here in a simplified plot where the vertical axis is region of interest, and then the horizontal axis is whether it goes higher or lower than its average activity over time. And so the real data is shown at the top left, and results from 2 different models are shown at the top right and bottom left. So if you look at those, you can see that the 2 models capture some aspects of this. There's kind of a switching between states. So that suggests that the structural resonance might have some importance. But at the same time, it doesn't capture the complexity of how the activity propagates across areas. So we think that this is not the full explanation. But that said, I have to mention that these models that we use based on DTI tractography don't include physical adjacency. And because we saw propagation along the cortex, that sort of actual physical adjacency might be important. So something we still need to explore. But meanwhile, going on to the other idea, this thought that maybe these are related to some sort of these deep brain nuclei that drive the thalamus and all of that through this reticular activating system, we took some rats and we gave them something called DSP4, which is a selective neurotoxin for the locus coeruleus. So it went in, it killed off most of the LC neurons, and then we scanned them, when it was effective about a week later. And when we did the QPP analysis on that, we got practically nothing. So we couldn't see any spatial organization. You can see the correlation vectors compared to the control rats over at the left. They're much weaker, much more spaced out. So we think that the DSP4 really disrupted these patterns, suggesting again that maybe there is a neuromodulatory role. Now, killing off the LC neurons is not subtle. It's a very sort of dramatic intervention. And so we might have messed up a whole lot of things. We're planning to go in and do some more subtle manipulations with optogenetics, but at least this gives us a clue that we might be going in the right direction. Okay, and part of the reason we think this is really interesting is that if you take out these quasi-periodic patterns, most of your average functional connectivity goes away. So these are something that's important. So I've plotted, again, this is for HCP data, the original functional connectivity at the top right, after regression of the QPPs at the bottom left. Now, The other thing, though, is that even after we take these out, you see some areas that are still very strongly correlated or still have strong anti-correlation. We haven't investigated all of those yet, but especially the ones that are strongly correlated tend to be interhemispheric homologs, left and right somatosensory cortex, left and right auditory cortex, things like that. So this suggests that something else is going on, more than maybe just the QPPs, maybe something else we need to look at. So as far as the QPPs go, we think that these reflect large-scale, slow electrical activity, probably linked to some sort of arousal system, and that they account for a lot of the functional connectivity that we measure. So going on to then another method, sliding window correlation and the brain states that we've talked about quite a bit this morning. There's quite a bit of evidence already that these are linked to neural activity. There's some great work by Katie Chang, where she did simultaneous EEG and fMRI and looked at power, say, in the alpha band versus the theta band, and saw that, you know, deactivation in one was associated with a certain pattern of connectivity shown over on the left, whereas activation in the other was associated with a different pattern of functional connectivity. So that suggests that this time-varying connectivity has some relationship, at least to these large-scale measures of brain activity. Again, these might be related to arousal levels. So there's a lot of work from Tagliazucci and Laus showing that if you look at functional connectivity in people who are falling asleep, or if you compare people who are awake or very drowsy, you see differences. And these differences line up very well to some of the differences that we see in standard sliding window correlation analyses with time-varying connectivity. So it might be that a lot of what we're pulling out is neural, but it's neural related to people getting sleepy. Okay, so then to go back to the rat for a minute, we've also looked into this question there. So we looked first at just the correlation between a single electrode and the bold signal from the area around it. And that's shown over at the left, so its color as a function of time lag. And what you should really notice is there's a lot of red everywhere. So basically, all of the frequency bands were really closely correlated to our bold signal. If you look for the very highest, it tends to be in the gamma band in this case. Now, we also then did correlation between the bold with a sliding window and compared correlation in bold. This is for the whole scan, so average correlation compared to the average correlation in the band-limited power in different frequencies. And in that case, we saw that delta actually was the best predictor of functional connectivity across areas. So that's a little bit strange, right? So gamma seems to drive the local bold signal the strongest, but delta is more predictive of the actual connections between areas. Kind of fits with a hypothesis in neuroscience that slower frequencies tend to mediate longer range connections. So we also then, of course, had to do the sliding window correlation experiment. So this goes back to the one I showed you very early on, where we managed to get the same results from, time courses paired from different rats. So now we looked at sliding window bold time courses from a rat compared to sliding window time courses of band-limited power recorded at the same time. And we did see very strong correlation between the changes in power in different frequency bands from the electrical signal and the changes in correlation from the bold signal. So in this case, I've lost my little asterisks that indicate what's significant, but the theta, the high beta, and the gamma are all significant contributors. So I think that kind of leaves us with a bit of a puzzle. We had gamma most locally tied to neural activity, delta mediating average functional connectivity, and theta, beta, and gamma tied to sliding window connectivity. I don't know what to make of that exactly right now, but I think it suggests that there are more things to explore that we haven't quite figured out yet. So we know that the sliding window connectivity is related to changes in neural activity. We're not sure if certain frequency bands are more important than others at this point, but we are pretty sure that vigilance plays an important role. Now, I will point out that when we looked at the data from the rat, those rats were anesthetized. and they shouldn't be undergoing changes in vigilance. So whatever changes we saw there are not related to, falling asleep or waking up. So it's a little bit different than in the human. But that suggests that there's still some sort of underlying variability even underneath these changes in vigilance. Okay, so my last topic, we've talked a little bit about co-activation patterns in individual events. So getting away from really the windowed approach to looking at individual excursions from baseline. So if you remember the co-activation patterns, you basically detect something that goes above threshold in an area you're interested in, and you look at what else activates with it. You can cluster those to get different patterns, etc. So what we did is instead of triggering on the bold time course, we used the simultaneously recorded LFP time course and made co-activation patterns based on when it went above threshold. And it turns out that it accounts both for most of the correlation between the LFP and the bold signal, and that we see a very similar sort of pattern as we get to the co-activation patterns obtained from bold alone. So up at the top left, you see LFP bold correlation first. That's the first column. The second column is our co-activation patterns made just by triggering on the LFP signal, which looks very similar. You can ignore the CDAP. That's just the co-deactivation pattern, which looks very much the same. Then we have the bold S1-seeded cross-correlation, the bold co-activation pattern, and the bold deactivation pattern. And they really all look very similar. So these individual events, that pass some sort of threshold, seem to really be driving the results, not just in the bold signal, but also neurally. So this is one of my last little pieces here. And what we did is we looked at bold amplitude versus LFP amplitude, all normalized and at the appropriate hemodynamic delay. And this is done in different frequency bands, so you'll see up at the top delta, theta, alpha, beta low, beta high, and then gamma. But what I want you to look at really is how much variability there is. So there's definitely a correlation. You can see the line that describes the correlation between the bold and the LFP power. But look at how much spread there is. So let's just take the broadband up here in the top right. If you look at a normalized bold of 4, so a very high bold excursion, you can still have LFP events that are below the mean. So there's a lot of variability here. We're nowhere close to the point where we can say that a high bold signal means a high neural activity. Everything is just done on a statistical basis. So why is there so much variability? I think it's a good question because it has implications for the fundamental resolution of resting state fMRI. Well, we know there's scanner noise, that's one. Physiological noise is a big one. And then this is kind of a hypothesis at the moment. I think we don't know exactly how much sloppiness there is in hemodynamic coupling. For example, what I mean by that is how much of an LFP excursion from its baseline does it take to make a bold signal? So over here on the left, I've drawn this kind of wobbly LFP with only one spot that hits my dotted threshold. Sorry, I found out I couldn't do these as we go at the last minute, and they kind of didn't transfer as well as I'd hoped. Over here, the hemodynamics, you may only get a change in response to that one super threshold event. So I think this is something that we still need to understand, is how tightly coupled are they? So the upshot for this, individual events do have a neural basis, but it's nowhere as consistent as we would like. So just in the last few minutes, I want to talk a little bit about complications. So we've talked about arousal a lot. Global signals related to arousal. QPPs are related to arousal. Sliding window correlation shows changes related to arousal. I didn't even talk about a paper from Turchi et al. And Neuron that came out last year about global signal and the basal nucleus of Maynard and how that can change the overall level of global signal. So there's a lot going on. These all seem to have some sort of relationship to some of the, maybe like the ascending activation system. So I think maybe there's common features. We haven't really teased those apart yet, but you can imagine that if you have a lot of QPPs or a strong presence of a particular sliding window brain state that's going to contribute to your global signal as well. So I think that's one of the challenges. How do we figure out what's related to what when large-scale patterns contribute to global signal, when widespread activity can mask or modulate activity at other scales, and when, in general, what we have to work with in humans, at least, is not really well localized. So we have this challenge if we want to try to pull apart different aspects of neural activity. So we've got just a few things we've tried to do. We tried to look at the relationship between quasi-periodic patterns and local neural activity. So we were looking for phase amplitude coupling, being the idea that if you looked at different phases of this infraslow QPP, you would see different amplitudes and higher frequencies. And what we found is that it's not necessarily there. So under one type of anesthesia, isoflurane, we saw it. Under another type, dexmedetomidine, we didn't. And so that suggests that this is not a fundamental property of the brain. We also did a dead rat. We like to do our dead rats as controls. You shouldn't get things in dead rats. So we also looked at, I showed this a little bit earlier, that the global signal has spatial variance, but the spatial variance doesn't look like the QPP, and we didn't see any evidence of QPP-like changes over time delays when we looked at the global signal. So we think if they interact, it's not dominated, at least, by the quasi-periodic patterns. And then we've also looked at, this is now going back to the sliding window correlation data between BOLD and LFP, we looked at doing that with and without global signal regression. And when we take out the global signal, we get better coupling between the BOLD and the LFP. So at least in our anesthetized rats where we acquired this data, the global signal is not helping the BOLD signal to reflect the underlying neural activity. So I think this is my last example. Some recent work that came out last year used a template that's very similar to one phase of the QPP to predict arousal. This, again, some of the original work was by Katie Chang. And then if you look at the simultaneous EEG-based vigilance from fMRI and compare the template prediction with global signal prediction, the template was actually a better predictor than the global signal. So it may be that the global signal predicts arousal because it's picking up some of the sensitivity from these large-scale processes. So I think just to summarize, all of the variants we've seen of time-varying connectivity have some relationship to neural activity. We think global signal is probably most related to baseline metabolism changes. The QPPs are tied to this infraslow activity and neuromodulation, and the sliding window correlation and individual events are more linked to frequencies across bands. We don't really know specific characteristics. So I think the question is, we know that these signals can carry something about specific tasks, but given the lack of real one-to-one coupling, can we ever expect to detect kind of these spontaneous occurrences that we would like to be able to pull out? So I put a whole bunch of references here in case anybody's interested. You can go and look them up later. Lots of different reviews, and I'm sure these will be posted online afterwards as well. So I wanted to acknowledge my lab and point out that we have some posters on related topics, one on global signal by Banaz, and then a couple on the co-activation patterns by Zhaudi. And last thing I wanted to put up, I wanted to point again to this repository for women in neuroscience. I wanted to point out that there is a family meeting bulletin board for OHBM this year. If you're here with kids and you're looking for activities or you have childcare to share, that's a great place to organize it. And we also have a group called Moms in STEM on Facebook. If you're interested, just send me an email. Okay, take questions.
So we have time for one quick question. Okay, if not, then let's thank Shella again, and Michael will be the next speaker.
Okay, we're just doing a bit of a computer swap over there.
Okay. So Michael Breakspear is an expert in dynamical models, among other things, and he will be talking about how we can model this relationship between the dynamics that we observe at a broad scale, in fMRI data, for example, and neuronal activity. So his presentation will be focusing more on the modeling aspect of this multi-scale nature of the time-varying functional connectivity. So.
Okay, thanks to Vince and Raphael for organising this. I'm just waiting for the computer to pop up here. I can't multitask because my brain is a potent mixture of jet lag and caffeine at the moment. So I'll just focus on one thing at a time. You what, sorry?
The file.
Okay, problem solved. Right, yes, as Raphael said, I'm going to go through a bit of a didactic overview of approaching this problem of dynamic functional connectivity from a modelling perspective. And so there's 5 parts to this talk. I'll assume very little baseline knowledge, and we'll take it from there. Okay, so basically we're doing brain mapping at the macroscopic scale, and in this area modelling is relatively new, but in neuroscience as a whole, modelling has a very rich and storied history. And in the 1950s, Hodgkin and Huxley won the Nobel Prize by developing a model of how a single neuron spikes. And I'm certainly not going to go through the equations, but they're differential equations. They're V to T, which is V the membrane potential. It's a conductance-based model of the neuron through which sodium, potassium and other ions flow in and out of the cell through voltage-gated ion channels. And that's all you need to know for that. And they derived and parameterized this model with very detailed neurophysiological recordings of the squid giant axon. And, you know, the longer I stay in science, the more it really amazes me what they did back in the 1950s. And it's a spectacular success, not just winning them the Nobel Prize, but still really being the starting point for computational models at the level of single neurons. But, you know, it's become a well-known story that we in brain mapping and also in cognitive neuroscience don't look at the scale of individual neurons, but recognise that neurons are embedded in local circuits like the hippocampus, which are themselves embedded in more complex regions, which then are embedded in the connectome. And theoretically, there's some very interesting computational arguments that said basically not only are spikes too weak to influence behaviour, but it's a very high-dimensional problem, almost ill-posable, and that if our thought and behaviour depended on precise timing of individual neurons, we wouldn't be robust cognitive and sentient beings. So it seems increasingly likely, and this is not necessarily popular right throughout all of neuroscience, that brain function is based on the ensemble behaviour of populations of neurons. Just like we vote collectively and sometimes make surprising decisions, so too do we now believe that different regions of the brain function more or less like a vote-based system, but not just the mean vote, but also the variance or the certainty of that vote. And also this population activity is matched to the apertures of the types of data that we look at human brain mapping. Okay, so I should have referenced this beautiful image. It's a science paper, it's certainly not ours. Here's a local neuron population, and I've got individual neurons as a spike raster here, and there's pyramidal cells and inhibitory neurons, and we could code this up. Even with a two-dimensional system, we've suddenly got a dynamical system of 2,000 dimensions, which is a very high-dimensional system to model. But if we just take 2 time points and window them and look at the distribution of neural states, this could be membrane potential, this could be other measures, we get these near Gaussian distributions. And so we do something called a mean field or Laplacian approximation, where instead of worrying about the states of the individual neurons, we just represent them as some sort of probability distribution. They don't have to be Gaussian, but we then dispense with just about all the information and just look at the mean, or you can think of this as the value of that population, and the variance, which is the inverse of the precision. And if we can do that at 2 time points and come up with something called a Fokker-Planck equation that actually properly predicts this forward evolution, then we've achieved this master equation approach. And this is quite novel in computational neuroscience, but it actually goes back decades. It's a very standard approach used in physics. And in fact, in many situations, to get going, we can just get rid of the variance or the precision and just look at the mean. And then we've got this relatively simple differential equation. So here's our complex neural histology. We could go to a slightly reduced model. This would be like the Human Brain Project, where we model individual compartments. We could model each neuron as a single point. This would be like a spiking neural circuit model. Or we can lump them all together and just model the mean states. So this is the process of mean field dimension reduction. And there's a much more interesting physical justification for this called the enslaving principle. And it's basically that neurons have these diffuse dendrites, so they actually filter and see this local mean field and to some degree become enslaved. So this synergistic principle of going in both directions here. Okay, what is this mysterious differential equation dx to t? Well, x is a vector of states, and f is the physiology that encaptures, in a Hodgkin-Huxley style way, how they behave. From a geometric perspective, we just look at the phase space that's spanned by the states, and f becomes a vector in this phase space. And then if we look at across all possible combinations of x and y, this is a 2-dimensional example, we get something called a vector field. These then link and yield orbits, which are smooth trajectories that are tangent to these vectors, and following some beautiful mathematics from Poincaré and others over 100 years ago, these flow onto underlying low-dimensional attractors. An attractor in this phase space yields the corresponding time series. So there's a one-to-one mapping between the type of dynamics and the shape of the attractor. So here's a simple attractor becoming more complex and bifurcating into something called a chaotic attractor. And you can see this intuitive connection between the time series and the attractor. So someone coming from mathematics like myself, this would be the starting or entry point for looking at dynamic functional connectivity. There's a bunch of these neural mass equations, and I'm just going to demonstrate one. It's pyramidal cells with slow inhibitory neurons, and here's a phase space representation of this mass in a burst and spike, sleep-like state. And if we tune some of the parameters, then this model can bifurcate into something called a chaotic attractor. Chaotic being deterministic because there's no noise in this model, but aperiodic. So it's one of these interesting mathematical entities. Then we're going to assume that's a parcel of the brain. This is a pretty crude approximation. And then we're going to allow these local populations to influence each other through this coupling function G through long-range white matter connections. So we have a chaotic attractor here, and then we put them right through the cortex, and we can put them in subthalamic cortical nuclei, and we're going to fire up, introduce either connectivity data either through something like COCOMAC, which is tracer-based studies and therefore directed, or we can use a connectome inferred from human diffusion imaging. And then we're going to see what happens. And a bunch of us have done this. I worked on this to begin with Chris Honey and Olaf Sporns, but Gustavo Deco, Vic Yersa, Petra Ritter, and others, including Leo from my group, have also worked on this. Is everyone else getting this strange resonance? It's rather unpleasant. Can you just hear if I talk like that, or is it being recorded? Okay, I'm going to just... Can you not hear me? Good. Okay, sorry. That's better. Good. So when we do this, and this is just one example, we got human connectivity data, we inferred connectomes, and we plugged in these models, and in front of us on these screens emerged these beautiful waves, rotating waves, breathers, and travelling waves. And I think OHBM last year, if you were here, was peak brain waves, but we did publish it in the meantime, and so all the information is in there. It's not a particularly unusual or unobserved phenomenon. In fact, now increasingly detailed descriptions of brain waves in different species, anesthesia, sleep, wake, and different types of recordings. And Shella spoke about these spatiotemporal patterns, so waves are certainly a canonical example of this. And why do we get waves? Well, Shella also talked about spatially embodied brain models. If you look at connectivity data, and this is a structural connectome, on the x-axis is distance, and on the y-axis is log of the edge weight, you get this exponential-like decay, and this is what in math we would call a synaptic kernel. And so you can see the closer you are, the more likely you are to be connected, and this then yields these waves. This is an example, if you were at OHBM in Hawaii, Terry Sanowski presented this, of waves in human spindle from ECOG data, and here's our modelled waves coming online a couple of years later. So we can be quite pleased with that. Top movie didn't work, but not to worry. What happens with waves, and this is the next thing I'll link more to dynamic functional connectivity, is that one wave pattern appears to be quasi-stable, and then after a short period of time transitions to another wave pattern, and then to another wave pattern. And if we use a measure of cross-correlation between the two hemispheres at each point in time, we can partition the brain into periods of low and high entropy. So that's something I'll come back to in a moment. This would be a model. Now these models are models of underlying neural states, unobservable for us outside the cranium. What we then do in this field is add an observation equation. And this is also quite close to what Shella was talking about, the relationship between neural activity, which we've modelled, and bold activity, which arises after a complex hemodynamic response process. But nonetheless, we used this model a couple of years ago to argue for a generative model of time-resolved changes in functional connectivity from the Human Connectome project, and that's from Andrew Zaleski. So this is like a forward or observation or generative model for what a lot of people in the field have been very intrigued with. Now, are these metastable states? If you look at the literature, you'll see things like dynamics, metastability, multi-stability, criticality. It kind of does your head in. So here's a little cartography of different types of stability from a math perspective. I spoke about attractors, which are like minima. How much time have I got, Raphael?
15 more minutes.
Okay, that's good. So we can think of a dynamical system of having multiple attractors, and they are like minima in this hilly space, and you can reformulate these dynamics as being a gradient descent in this space, and then if you put noise into the system, you will get jumps from one attractor to the other. Each attractor could be quite complex or quite simple, but in this state you need noise, and then the system will reside in the vicinity of one of these attractors, and then in the presence of noise jump into another attractor. And that yields a particular fingerprint of how long the system dwells in these different types of states. A metastable state is one in which there's really no attractors, and you can see that here, that each of these fixed points has flows attracting into it, and also at least one flow expelling from it. So these are saddles. So this is like an Escher diagram where there's no final resting place. The system goes towards a saddle point, and then as it approaches, hits one of these unstable manifolds and goes off to the next. So this is the formal definition in mathematics of metastability. And then in a critical system, there is a single attracting fixed point, but the point is it's very, very weak. So once the system approaches the fixed point, it really slows down and gets highly influenced by the presence of noise. And these are completely different dynamical scenarios. They can arise in the same system, but they give rise to very different spectral and other stochastic properties that you can then use to disambiguate whether your system of interest is multi-stable, metastable, or criticality. And I just would like to see some of this nomenclature enter the field and discourage people from using these terms interchangeably. Okay, so what about our brainwaves? So here they are evolving in time. We do the Hilbert transform, and this work was done by James Roberts, at each time point, and look at a gradient of phase from each point, and then in a tractography-like way create streamlines and look at the sources and sinks. So here's an example of a movie. And what you see is even though the waves are quite dynamic, the underlying gradients, the vector field is quite stable, and that corresponds on the right there to a set of sinks and sources, and sometimes the sinks and sources are spirals. And then during a transition, they bump into each other, and the whole state becomes quite turbulent and then transitions to another low energy state. So here's another example of this. Here's a stable one, and then a transition with a high entropy state, and then quasi-stability of a new spatiotemporal pattern. I should say this, in our system, if I could go backwards, which I don't think I can. Nope. I can, okay. This bumping and colliding of saddles and sources and sinks is consistent with what I showed before about metastability. So this model is a model of metastable brainwaves. Now another thing that we did was to look at recurrence plots. I think Shella spoke about this, and I know Katie Chang is giving a keynote and also did this. What we basically did here is take this whole vector at one time point and then correlated it with something called an inner product with all the vectors at other time points, and that's what you see here, time on the x and y axis, and you see these off-diagonal high correlations in our empirical. It's not empirical data, it's from the model. And then Manjari spoke about null models. We generate a null model on the right that preserves all the linear properties of the data, and we look at the recurrences of those, and we can look at this bootstrap null and distribution. We can see our model is well outside this stationary linear null, and you can use that as a threshold. So we got quite excited when we saw these brain recurrences being generated by our model, because these have been described in the literature. And there's other information in the paper that links our model to different aspects of MEG from Mark Ulrich's data and fMRI data. Now we can change different parameters. Here's our waves. These are clustered states with different combinations of time delays and coupling. And I think this is what a lot of people probably think of when they think of dynamic functional connectivity. They think of a brain transitioning between different clusters, and we can have a combination, which is clusters within which there's waves. So our model, if you look across all parameters, it gives this whole variety, this sort of zoo of dynamic patterns. Clusters, whole brain synchrony, waves, and lurching waves. And so now we're in the process of doing model inference, model inversion, and parameter estimation. I just got to speak for a few minutes about open source simulation engines. There's a beautiful one I saw Paula here before, Sans Leon, the virtual brain. It's all Python. You can download it. You can become part of quite a big community. I highly recommend that you do that. After years of fielding questions from people asking me to share my fairly badly written MATLAB code, I worked with Stuart Heitman, who's a software engineer and writes beautiful code to do basically a very simple toolbox of dynamical models, but coded up very smartly. This is called the Brain Dynamics Toolbox. I know MATLAB's not very popular anymore, but it's beautifully written by Stuart. It's well commented. It's all completely accompanied by how to use manual. So if you're interested in learning about these models, you can download that. Okay, now in the last 5 minutes, I guess, I thought we'd hear more about confounds in dynamic functional connectivity, and I know Shella touched on it, but we can use models to go beyond this. Is a physiological correlate in bold, is it a confound, or is it part of changes in arousal? And this is modelling brain and body. This is a friend of mine. He's a computer scientist. We did some work together some years ago, and he was a test in this. So Roland here is watching a stand-up comedian, and the point about this is, okay, it's natural vision, but there's this highly dynamic changes in mood, affect, respiration, cardiac activity, all coming in joint unison with the brain. So it's a little bit like this. You've got the brain with the EEG data, and then you've got physiological systems. And these can also be modelled, and they both yield noisy data. So the top one is some stereo EEG from the insula, from some colleagues in Brisbane, and the bottom is cardiac interbeat interval. They look noisy, but if you look at the time scales, you see one is much slower than the other. So if we stretch out them to have the same time series, you see that physiological signals tend to be a lot slower than brain signals. In this study, we uploaded some data from Germany. It was 7T data of the mainly the temporal cortex of people listening to Forrest Gump with a narrator. We extracted the sound envelope, and if we regress that, get the superior temporal gyrus. This is work done with Vin Nguyen some years ago. But if we take the interbeat interval or the heart rate variability and convolve that with the canonical HRF, we got very specific activity in the posterior insula. This is not the cardiac signal per se, this is the derivative of the cardiac signal. So the point of that slide is that, the brain seems to have a fast filter for perceptual or extra perceptive activity, and a slow filter for physiological or interoceptive activity. And this paper goes on, a lovely paper by Vin, to look at how they're integrated in the anterior insula. So I've touched on dynamical systems, I've touched on coupled dynamical systems, and more recently I touched just then on fast, slow systems. These are coupled systems in which you have kind of a separation of timescales. So the X here would be the brain states, and the Y would be the physiological states. And you can see this denominator tau, which slows down the other system. And this is another area with decades of beautiful work in physics and maths on timescale separation. So a couple of years ago, Leonardo and Goyo and I thought about this, and we proposed that the brain was actually composed in a way with this so-called chronoarchitecture, that there would be fast extra-perceptive systems in the periphery and slow interoceptive systems in the cortical hubs of the brain, like the insula. Okay, that finishes my talk. That's the group of mine, and also now Luca Cocchi and James Roberts, 3 groups at a retreat in Byron. And if you are interested, most of the data, all the simulations, the Brain Dynamics Toolbox can be downloaded. And yes, there's a number of related posters, including this code you can get for pulling out waves in your own data that Paula Sanz-Leon will be presenting. We've used these models for brain stimulation. There's a fancy new way of doing this modelling called eigenmode decomposition. You can look at models of synchronization and also bistability. So I'll end by asking for a few questions. Okay. It was the time delay between different nodes. So one axis was the coupling strength between nodes. I think my talk's gone forever now. The x-axis, I mean, we don't really know what the time delay is, and this is an issue. So we couple all nodes in the system with a 10 millisecond time delay. We can couple them, and we have, with a time delay that's proportional to the distance between the nodes. That just makes the numerical simulations a lot slower. And we can also couple them with, even if the areas are the identical distance, with a dispersion in the time delay. But these are just adding more and more levels of complexity. If you do that, you tend to get slower waves. And our waves tend to be about an order of magnitude faster than the waves that I glossed over in the slide before. So probably this dispersion of time delays would slow the waves down to the speed that are more commonly observed. But sorry, I think my talk's disappeared.
So you were also changing the function of the coupling, not just the amount of coupling.
No, we didn't change. We kept the coupling the same. In that particular model, it's excitatory coupling at AMPA-mediated excitatory neurons. And the stronger the influence from an external node, the weaker the influence from local excitatory feedback, so that the pyramidal cells see the same overall influence from other pyramidal cells. Otherwise, as you increase the coupling, you're just increasing the overall excitation of the brain. So we counterbalance that in this model. Yes?
At the beginning of the talk, you say that all these dynamic models could influence like structural connectivity and vice versa. Have you tried to include these priors or these constraints about the structural connectivity from DTI or something in these theoretic models?
In which model, sorry? Yeah, this is what I did in this. I think I glossed too quickly over that. We took diffusion imaging data from 200 healthy controls. We reconstructed whole brain tractography, and we had parcellation of the brain in, I think, 500 different mini regions, and then we allowed them to be influenced through whole brain human connectivity. So the connection to connection was proportional to the streamline count normalized to the distance. But we've also done this with macaque data, where you get directed connectivity.
Okay, so let's thank Michael again.
Do you have one more question?
Okay, sorry, I didn't see.
I threw together data from a whole different types of modalities, including intracranial stereo EEG, MEG, EEG, and fMRI, just in various patches through the talk. I'm not an expert in source reconstruction of EEG or MEG data, so I'd be, obviously, like everybody, a little bit cautious about inferring sources in insular and other deep spaces that are highly mixed in sensor space. However, the way we proceed is we have a generative model and a forward model, and we invert the whole model. We don't take the data and do source reconstruction and then just compare our model data to source reconstructed data. Well, we have done that, but the bigger goal is to invert the entire model with the generative model plus the observation model, in which deep sources would contribute very little to the observed data, and therefore to something called the likelihood function. Anyway, thank you.
Okay, thank you, Michael. And the next and last speaker for today is Dan Lurie from Berkeley, who has been leading the writing of a review on this topic of dynamic functional and time-varying functional connectivity, and so he has been at the heart of kind of merging all these contradicting viewpoints from time to time, and he will discuss the open challenges and open questions that remain in the field. So Dan.
Great. Well, just thanks so much, Raphael and Vince, for having me here. I'm really excited to be talking with you and to be sharing this session with a number of people whose work have really influenced the way I think about brain dynamics. And I think this is a really promising research area for scientists interested in understanding large-scale brain dynamics and their relationship to behavior. And there are many, many more controversies than we've talked about today or that I can cover in this talk. As such, I just want to bring your attention to our paper that discusses these issues in more detail. If you go up, it's on SciArchive. It's hopefully out soon somewhere. But this paper actually began at OHBM in Vancouver 2 years ago, where there's an open discussion. It's kind of evolved into what I think is a really nice review of the issues that we've been talking about today. And I want to emphasize that I'm the one standing up here, but this was really a team effort by this really amazing set of co-authors. And everything that I talk about today will be covered in much more detail in the paper. So if there are questions you have about references or things like that, feel free to ask me, but there's going to be a lot more detail in there. So I think let's just get started with like an idea of what we're going to be talking about today. So my talk will be in two parts. In part one, I'll review the diversity of methods for studying fMRI time-varying connectivity, and I'll guide you through the landscape of models and analysis approaches and how they relate to each other, discuss how different approaches provide different complementary insights into brain dynamics, and give a few ideas of things to consider when deciding on a TVC analysis strategy. In part two, I'll dive into a few of the controversies and open questions in the field, which I think are most salient and interesting. So let's get started. If you're going to only remember one idea from the first part of this talk, I think it should be that there's no single best method for studying time-varying connectivity, and that different modeling and analysis approaches provide complementary insights into brain dynamics. To get a sense of what I mean here, I think it's useful to take a few minutes to explore the landscape of ways which one might study time-varying functional connectivity. And this will allow us to get a sense of the high-level overview of how different approaches to studying time-varying connectivity relate to each other. So because we're talking here about resting state fMRI, we're going to start with the bold fMRI time series, but a lot of these methods could equally be applied to electrophysiology data, or EEG, or even calcium imaging. And so from these bold time series, there are a few different analysis endpoints we might be interested in. So we might be interested in studying the time-varying properties of a particular connection, perhaps between two regions of interest, selected based on a specific hypothesis that we have about brain function or cognition. We could test the observed fluctuations against various null models. We could calculate summary measures like the mean and variance of the time-varying connectivity, or attempt to relate the fluctuations in connectivity to some other simultaneously recorded measures such as behavioral performance or measures of peripheral physiology. Moving beyond single connections, we might be interested in how patterns of whole brain connectivity change over time, and in measures from network science which summarize these patterns in the reconfigurations. If we take a state-based perspective on brain dynamics, we may be interested in measures like switching rate, state occupancy, or dwell times. And as with this case of single connections, we can compute brain state summary measures and compare them to null models to assess their time-varying properties. Now finally, as Michael just reviewed in the previous talk, we might want to try and actually model and understand the fast timescale nonlinear neural dynamics that underlie the brain activity that we're able to measure with fMRI. And so at this point, we have a starting point, the observed bold time series, and a number of possible analysis and modeling endpoints. And so the question is, how do we get from one to the other? And so we heard early on in the beginning from Giulia, sliding window is most likely the most common method for estimating time-varying connectivity. It's already being discussed in a little bit more detail, but as a review, this method involves just estimating time-varying connectivity by computing the correlation between two time series over successive windows. And once we have our estimates, we can calculate a number of summary measures. Now, importantly, however, the sliding window approach is by far not the only way to get to these metrics. So there are a wide range of other analytic approaches which also produce estimates of time-varying connectivity. And I don't have time to review them all here, and many of them have been mentioned already, but there are some examples like hidden Markov models and time frequency-based approaches. The critical point is that they all eventually produce estimates of time-varying connectivity that are in many ways functionally equivalent to those that result from sliding window correlation. That said, each method has its own particular assumptions, strengths, and weaknesses, and this is an important point that I'm going to come back to in a little bit. So moving from the case of individual connections is simply a matter of calculating time-varying connectivity between all pairs of time series. And again, this can be done using a variety of methods. And once we've estimated whole brain for time-varying connectivity, we can begin to explore the time-varying network properties. And now these network properties can also be applied to brain states, which like TVC, can be estimated in multiple ways. So some methods, such as hidden Markov models, estimate states directly from the observed bold time series, where other common approaches involve clustering whole brain time-varying connectivity patterns, such as those calculated via sliding window correlation. And in either case, once we have our brain states, we can explore their time-varying properties. And then last but not least, studies of brain dynamics using biophysical models typically involve fitting the model to real brain data in order to set model parameters, which can then be interrogated for insights into the mechanisms underlying observed brain activity. And while this particular schematic depicts biophysical models as their own workflow, it's increasingly common to see modeling integrated into analysis of real brain data, and the use of these approaches in combination can provide powerful insights. So as you can see, the landscape of possible analytic and modeling approaches for studying time-varying connectivity is relatively large and complex, with multiple possible routes to the same analytic endpoint. And while it's generally difficult to cleanly categorize these approaches, it can be useful to make a basic distinction between data-driven approaches, such as those on the right, which analyze the properties of the observed bold time series without explicitly modeling the underlying neural dynamics, and biophysical models on the left, which focus specifically on these dynamics. Another way to distinguish between these methods is to break them down by what kind of insights they can provide us about brain dynamics. And so going back to this point, that different approaches provide different insights. So closest to the raw data are the estimates of time-varying connectivity. So these allow us to explore the relationship between momentary functional connectivity patterns, and other time-varying phenomena like cognition or behavior. Models of brain states and their transitions allow us to investigate network properties of transient brain states and how they reconfigure over time. Comparing observed TVC estimates or summary measures derived from TVC estimates or brain state models allow us to test specific hypotheses about the temporal properties of neural time series. And then finally, biophysical modeling allows us to test mechanistic hypotheses about the phenomena that give rise to TVC and to explore the complex neural dynamics that may underlie the observed brain activity that we see with fMRI. And so given this diversity of methods, it can be difficult to decide which approach to use, even for those of us who are really familiar with these methods. So here are just a couple of things that I think are useful to consider when deciding on a TVC analysis. So there may be no single best method for studying TVC, and in addition to the fact that different methods can provide different and complementary insights into brain dynamics, each method also has its own set of strengths and weaknesses and assumptions. As such, the choice of what TVC method to use in a given situation often involves balancing trade-offs, and your choices should ideally be informed by your specific questions, your hypotheses and goals of your study, and the available data. So in terms of model assumptions, a good example is to consider the sliding window correlation approach versus hidden Markov models. So sliding window methods make a number of assumptions about the statistical properties of the time series data, but no assumptions about the temporal structure of brain dynamics. Hidden Markov models, on the other hand, specifically assume the presence of latent brain states when estimating time-varying connectivity, and that transitions between these states follow particular rules. Estimating brain states by clustering sliding window connectivity matrices doesn't involve making the same assumptions. Now, none of these approaches is necessarily better or worse than the others, but their differences can potentially impact your results, and you should keep this in mind when deciding which to use. So just to kind of review what we've talked about so far, there's a really rich landscape of methods for studying time-varying connectivity, and different methods provide different complementary insight into brain dynamics, and that when you're deciding on which method to use, you should think really carefully about what theoretical question you're trying to answer, because which method you use will determine whether you're actually able to answer the question that you're trying to get at, or will be trying to kind of force a square peg into a round hole. So in part two, let's take a few examples of the controversies and outstanding questions in the study of resting time-varying connectivity. So first, I'll discuss the impact of arousal on brain function and behavior, and try to make the case that fluctuations in arousal should not be considered a confound. Second, I'll present evidence that both for and against the hypothesis that resting time-varying connectivity is related to ongoing cognition. And third, I'll detail how differences in data cleaning can impact time-varying connectivity analysis. And then I'll finally take a few minutes to talk about one way to think about the relationship between static time-varying connectivity and static connectivity and time-varying connectivity. So as we've heard from Shella, fluctuations in arousal can have a major influence on brain function and the measures of brain function. So as neuroscientists, we're ultimately interested in understanding what processes give rise to the varied neural phenomena we study. And so resting bold time-varying connectivity is certainly the result of a number of different underlying processes, ranging from intrinsic homeostatic processes all the way to brain activity supporting complex cognitive operations. And whether or not any one of these factors contributing to time-varying connectivity is considered a signal or noise really depends on the specific question being asked. And like Shella, I think that the global neural signals like arousal are a great example of this, especially in light of questions about the extent to which bold time-varying connectivity at rest is related to ongoing cognition. So this is a figure from a paper from Katie Chang from a few years ago, and what it shows is a simultaneously recorded fMRI local field potential and a behavioral index of arousal. And you can see that the behavioral index of arousal tracks the fMRI arousal index really well. And when you look at the percent of the variance that you can explain in the bold time series by this behavioral measure of arousal, depending on the region, you can explain up to 25% of the variance. So arousal is this global neural phenomenon that is really driving a lot of the change in what's happening in the brain over time. And I think kind of importantly, these flexions and durations in arousal are not just, they're not neural and non-relevant to cognition. They also are really important in our cognition and behavior. So this is another study from the same year in which the authors looked at dynamic connectivity states that were associated with either an eyes open brain state, which they considered a high arousal state, or an eyes closed brain state, which they considered a low arousal state. And they measured this by looking at how open their eyes were. And so low eye scores are those in which the eyes are almost closed, and high eye scores are times when the eyes are wide open. And as you can see, in the eyes open brain state, you're more likely to spend time in this eyes open brain state when your eyes are fully open than when you're in the eyes closed brain state, and vice versa. But what I think is most interesting about this is that if you look at the probability of each state occurring during an auditory vigilance task, the number of times that you lapse in this task in which you have errors is correlated with the proportion of time that you spend in this low arousal brain state. And it's negatively correlated with the amount of time that you spend in this high arousal brain state. And so I think this kind of underscores a lot of work that has been done in the past, showing that arousal and these other global neural processes are really kind of fundamental to driving both behavioral variability and changes in cognitive function. Now, if we think about this for a second, it actually makes a lot of sense. So level of arousal, as Shella said, is largely driven by ascending brainstem neuromodulatory systems, which have widespread projections throughout the brain. Local and global release of neuromodulators has been repeatedly shown to have major impact on the dynamics of neural circuits, and it's been suggested that activity in these systems may be responsible for driving reconfiguration of functional brain networks. Given all this, it would be surprising if fluctuations in arousal were not closely related to time-varying aspects of brain function. From this perspective, far from being a confounding factor, fluctuations in arousal are an integral part of the phenomena of the systems and cognitive neuroscientists seek to explain. So the takeaway from this is that fluctuations in arousal have a major impact on brain function and cognition. And I think a lot of people, certainly in cognitive neuroscience, are really interested in time-varying connectivity at rest because it might offer an opportunity to study spontaneous and kind of self-directed cognition in a way that is not so easily accessible by other methods. And that we should think really carefully about whether these arousal and these global neural phenomena, whether someone's sleepy, whether someone's dozing off in the scanner, are really confounds. They may not be directly related to your question about working memory or perceptual vigilance or emotion processing, but they're really contributing a lot to the processes that are supporting the cognition that you're interested in. And so speaking about this desire to try and look at how we can potentially use time-varying connectivity to study these spontaneous cognitions, like mind wandering and daydreaming during the resting state. This is just one example of a recent study by Aaron Cucci, one of our co-authors, that looked at the connectivity between the posterior cingulate cortex and the medial temporal lobe subsystem of the default mode network. And what Aaron did is he had people during a painful stimuli paradigm in which they were experiencing painful stimuli, he asked them repeatedly throughout this experiment how often they were paying attention to the pain versus something else. So every couple of minutes, he would ask them, what are you paying attention to? And this is called experience sampling or thought probe methodology. And when he looked at the static connectivity between these areas, he was unable to find any relationship between the amount of time that you were spent thinking about this painful stimulus versus thinking about other things. But if you look at the variability of time-varying connectivity, you can see that this does have, you do see a relationship, which goes back to a point made earlier, which is that for certain types of cognitive processes that fluctuate over short timescales, it may be that time-varying connectivity is more sensitive a measure than static connectivity. And so that provides a little bit of evidence that perhaps time-varying connectivity, even at rest, when we're not showing overt behavioral changes, is sensitive to the dynamics of cognition. But counter to that is the fact that, as Shella was talking about, many of the studies of the neural basis of time-varying connectivity were done in anesthetized animals. And so this is a figure from one of the papers from her group, which shows simultaneously recorded electrophysiology and bold fMRI, where you have the sliding window correlation on the y-axis, and over time, you can see that yes, you get time-varying connectivity both in these electrophysiology frequency bands and in the bowl signal. So this is a little bit concerning. If we're interested in trying to use time-varying connectivity to study cognition, then a state like unconsciousness in which we wouldn't expect cognition to be occurring shouldn't show these types of fluctuations. And I think there's a little bit of nuance to it, because if you look at the dynamics and the properties of the time-varying connectivity, though it still exists, it does change. This is actually one of the earlier papers on showing time-varying connectivity in humans and macaques that shows that the number of unique states that you visit and the number of transitions that you have between states decreases as you deepen, as your level of anesthesia deepens. And so while time-varying connectivity does remain during anesthesia, something about the properties of these phenomena is changing. And trying to pull apart what exactly the properties are that are sensitive to the things that you're interested in, whether it be cognition or behavior or clinical aspects, and which are related to these other factors which are contributing to the signal, is something that as a community we really need to work on, because as Shella said, there are so many things that contribute to it. And if you are trying to make a claim about the necessity of a relationship between a time-varying connectivity measure and your other measure of interest, it's important to make sure that it's not being driven by something else. And in terms of being driven by other factors, something that if you work with functional MRI, you're all too familiar with is this idea that we need to really denoise our data. Functional MRI, the signals that we're looking at are often, single-digit % signal changes, and in fMRI functional connectivity in particular, motion is a really pernicious problem. And so there's been a lot of talk in functional connectivity literature over the years about the impact of motion on estimates of functional connectivity, and that holds true for time-varying connectivity as well. There's been a number of papers in recent years looking at evaluating a very wide range of pipelines for what is most effective at removing the effect of noise on static functional connectivity. And this is the recent paper doing the same thing for one aspect of time-varying connectivity, which is the flexibility of a region's affiliation between different functional networks over the course of a scan. And as you can see, the different denoising pipelines have very different efficacy in terms of removing the residual effects of motion, with some pipelines showing essentially no residual effects of motion, and some pipelines like ICA or Aroma, which for static functional connectivity is generally believed to be one of the most effective pipelines at removing residual motion effects, not being quite as effective. And so motion isn't the only thing that comes in when we're doing denoising and data cleaning. Temporal filtering is something that we talked about at the beginning of the session in terms of what filtering should you be doing and how should that filtering influence your choice of window length if you're doing a sliding window correlation. So this is an example from a project that I'm working on and collaborating with people at Berkeley. And so what we're doing is we're applying a hidden Markov model which essentially tries to find brain states in resting fMRI data and looks at the probability at each time point that a state is active. And so because we wanted to make sure that our results were robust, we did this analysis through 2 different pipelines. But crucially, the pipelines were almost identical except for their frequency bands. Every other aspect of the pre-processing in terms of what our nuisance regressors were, in terms of like whether we included global signal or not, was identical. And so if we look at this state time series in which on the x-axis we have time and the y-axis we have states, you can see that the yellow is times at which that state is most likely to be active. This is through one pipeline with a temporal bandpass filter of 0.008 to 0.09 hertz. And if we look at this other pipeline, which is identical except for a couple of tenths or hundredths of a hertz difference, you show very different dynamics. And we think that this has to do not just with the small differences in the bandpass frequencies, but in the way that the filter is actually implemented. And one is using a discrete cosine filter, one is using a Butterworth filter. We're still trying to trace this up, but it suggests that when you're dealing with these dynamic phenomena, very small differences in how you're treating your data can make a big difference on the back end. And so that's just kind of one example of how pre-processing decisions can have a major impact on the results of TVC analyses. And while we have come a long way in the static connectivity literature in terms of figuring out what are best practices, what kind of denoising do you need to do for motion and other types of signals, it's still early days for time-varying functional connectivity. And there have only been a couple of papers that have looked at this really systematically. And until we are able to ensure that our results are not driven by differences in denoising strategies, it's going to be hard to come to a consensus on the extent to which time-varying connectivity is associated with clinical differences or cognition. The final controversy that I want to talk about today is one that's a little bit more conceptual, and it has to do with the fact that static functional connectivity networks are really stable. And this has been a really good thing for a long time. One of the benefits of resting state functional connectivity is that you can scan someone a year apart, and their connectome will be so similar that you can identify them in another group of people. And that's great. It means that it's a stable biomarker measure. It can be used to perhaps distinguish people based on disease state. But at the same time, it suggests that the resting state functional connectivity is maybe not so sensitive to the kind of changes in cognition that many people are interested in. So this is a figure from a paper from Michael Cole from a couple of years ago showing the functional connectivity patterns from a number of different tasks. And showing their similarity both to each other and to the resting state. And the correlations are really high. And this and other papers have estimated the correlation between your patterns of functional connectivity at rest and during task execution can be up to something like 0.9. And this is pretty well replicated across studies. And so then the question is, if we're seeing such stable patterns of static functional connectivity, even when we are doing overtly different states, when we're doing a relational task versus a gambling task, something that is really kind of pushing us to use different types of thoughts, why should we expect to see changes in time-varying connectivity structure during a period of rest in which you're just sitting in the scanner, you're not being told to do different things, and maybe the only difference is that you're kind of mind-wandering about different things in different ways. And I think the resolution to this has to do with something that came up earlier, which is the idea that static functional connectivity is a summary measure, right? And like any summary measure, it's an aggregate measure. This aggregate measure of static functional connectivity is likely going to fail to capture some aspect of the underlying dynamic phenomena. An example of this is that the same pattern of static functional connectivity might result from different spatiotemporal patterns of underlying time-varying connectivity. And I think this has to do with the fact that brain dynamics and behavior unfold over time in a particular sequence, right? The words that I'm saying to you would mean something very different if I said them backwards. And in the same way, the trajectories which my neural systems take through time are meaningful, and that if we permuted them, they're not time invariant. And so this means that even if you have the same distribution of static connectivity, of connectivity states, they can have very different temporal profiles. So an example might be if we have two brain states, brain state A and brain state B, and they each show up 4 times. Well, you could have them show up like this, in which there's kind of a block structure, or they could show up interspersed, or they could show up in a kind of a mini block structure. And you can think about this as an example of, instead of 4 states, maybe you have 180 volumes, or you have an hour of resting state data. And if you average over this time, you may see, well, there's an equal number of A's and B's in each case, but the dynamics and the temporal sequence in which they occur is different. And that's going to be meaningful if we think that the mental capacities come from brain activity. And so I think that it's important to go beyond just identifying functional connectivity patterns at a high temporal resolution. I think that there's a lot of utility in trying to see what are the momentary functional connectivity patterns associated with specific cognitive processes, like what is the delay-related functional connectivity pattern during a working memory experiment. But to really understand the brain dynamics and how they give rise to cognition and behavior, we need to understand how they unfold over time. And so I think this is just kind of one way of saying that resting state time-varying connectivity is consistent with stability of static functional connectivity, and that the temporal structure of time-varying connectivity fluctuations may be key to understanding brain dynamics and how they relate to cognition and behavior. So just to kind of wrap up quickly and talk a little bit of like what we've learned and what we don't know yet. There's a really rich landscape of methods for time-varying connectivity, and there's no one best method. And they provide complementary insights into brain dynamics. If you're going to be choosing a time-varying connectivity analysis, I'd say work backwards from what your hypothesis is and how you think the brain works. If you think that the brain visits distinct states, then maybe go with a state-based approach. If you don't think it visits distinct states, maybe try another approach. And we don't know the ground truth answer to this. And so there's really utility in using both of these methods and looking at how they provide different insights and different evidence about the brain phenomena that we're interested in. We talked about how fluctuations in arousal are likely a major factor contributing to bold time-varying connectivity, and that arousal may drive behavioral variability and functional reconfiguration, and you should think really carefully if you consider arousal a confound. We talked about how there's emerging evidence that resting state time-varying connectivity is relevant cognitively and behaviorally, but that important questions remain about this relationship. It's clear that there are some aspects of time-varying connectivity that remain during states of unconsciousness in which we would expect no changes in cognitive state at all. We talked about how preprocessing and denoising can have a major impact on the results of time-varying connectivity analysis, and that we're really lacking consensus best practices for many of the components of the denoising pipelines that we need to use to make sure that our data is robust. And finally, we've talked about how stable patterns of static functional connectivity are conceptually consistent with time-varying connectivity that changes during rest. Just because static connectivity patterns are relatively stable between overtly different task states doesn't mean that their underlying temporal patterns are the same. And so with that, I just want to acknowledge mostly these wonderful co-authors who have worked with me for the past 2 years on this paper. I think they've put an immense amount of work into it. And in particular, I wanted to thank Dan Kessler, who wasn't able to be here, and Vince Calhoun, who were both kind of helping me organize this effort and wrangle this huge list of co-authors. I want to thank my lab at UC Berkeley, my funding, and just a plug for my poster, which has nothing to do with time-varying connectivity, but a lot to do with dynamics. And if you're interested in timescale stuff, you might want to come to that on Monday afternoon. And I'm happy to take questions.
Okay, so thanks then for this very nice conclusion of the course. We have time for a few last questions, if any. And if not, thank you very much for attending the course. Please provide feedback on the app if you have anything to say. It's always nice to have this feedback to prepare the courses. And please join me in thanking again all the speakers of this course.